slow science, soft stories, peaceful nights. Welcome to Lina's Night Lab. What if I told you that reality doesn't actually exist until you look at it? From particles that exist in multiple places at once, to cats that are simultaneously dead and alive, prepare to have everything you thought you knew about the universe completely shattered. Whether you happen to be resting in a silent, dimly lit bedroom, dozing gently on a late-night commuter train, or relaxing on a soft sofa while holding a soothing cup of warm tea, I hope you feel completely secure and perfectly at ease. Settle in comfortably and prepare to let your mind wander peacefully into deep, quiet contemplation this evening. I will do my absolute best to keep our subject matter from being overly stimulating tonight, so you can easily drift off to a deep and peaceful sleep. However, if these fascinating concepts end up keeping your eyes wide open, you will at least walk away knowing exactly why tiny bits of matter occasionally behave like ripples in a pond. You will also discover why the physical universe appears to pause and wait for a conscious observer before finally making up its mind. Losing a little bit of rest is certainly a very fair trade for unlocking those profound mind-bending secrets of the natural world. With that trade in mind, let us dive in and ask, what exactly is quantum physics, and why does it feel like the cosmos is just improvising its rules? Our everyday physical environment, the world we interact with, appears incredibly stable and predictable. A released teacup plummets, a tossed coin lands, and the moon remains in the sky even when we look away. However, as the 20th century dawned, researchers started examining nature on a much tinier scale. The further they zoomed into the building blocks of matter, the weirder the universe acted. They found light could act as both a wave and a particle. They realized tiny bits of matter could occupy multiple locations simultaneously until measured. Furthermore, simply observing a phenomenon did not merely uncover a pre-existing state, it actively altered the outcome. These bizarre findings were certainly not the result of faulty instruments or sloppy calculations. The results were genuine and consistently repeatable, completely breaking the neat, centuries-old rules of classical mechanics. Rather than just adding a fresh subfield to science, quantum mechanics introduced an entirely new perspective on existence. It revealed a glittering domain where absolute guarantees give way to likelihoods, and causes do not reliably trigger effects in our familiar sequence. We will glide smoothly through this landscape together. You will not have to memorize complex formulas or historical figures. Instead, we will take our time, unraveling a single enigma after another, from the initial anomalies that knocked researchers off their traditional pedestals to the current mysteries depriving modern physicists of sleep. So get comfortable, shut your eyes if you prefer, and prepare to journey into a realm where absolute voids are actually full of activity, and every fact you believe about existence is only probably correct. Before we embrace that uncertainty, we must look back. As the 1900s began, science felt incredibly finished. Researchers had neatly organized thermodynamics, fully grasped motion rules, and perfectly fitted light into electromagnetic theory. This era was a golden period of absolute confidence. Many experts genuinely thought they had solved every major mystery. They assumed the only tasks left were minor details, much like wiping tiny dust specks from the corners of an already spotless room. But one of those tiny specks hid a massive puzzle centered around a basic question: what exactly occurs when an object gets hot? If you warm a chunk of coal or a piece of metal, it starts to emit light. As the temperature climbs, this glow shifts from red to orange and eventually to bright white. Scientists called this black body radiation, describing the electromagnetic waves released by a hot object. Watching this was straightforward, but explaining the mechanics proved incredibly frustrating. The established rules of classical physics completely broke down here. Using standard mathematical models, physicists calculated that a hotter black body should release exponentially more energy at shorter wavelengths, specifically in the ultraviolet spectrum. However, this created a massive flaw. The formulas suggested energy output would become infinite at the highest frequencies. Because this outcome was physically absurd, researchers dubbed it the ultraviolet catastrophe. No matter how much they adjusted the traditional equations, the calculations always devolved into absolute gibberish. The physical world was clearly behaving differently than the theories suggested, proving a crucial piece of the puzzle was still missing. To find that missing piece, we have to turn to Max Planck. Back in 1899, this German theoretical physicist was famous for his meticulous approach rather than any rebellious streak. He actually trusted the traditional classical framework completely, yet he possessed a highly practical mindset. So, when the black body radiation dilemma landed on his desk, he took a subtly groundbreaking step to make the mathematics align. Planck proposed a bizarre little concept to correct the formulas. He wondered if energy release was restricted to specific amounts rather than flowing freely. Think of it like a coin that you simply cannot break in half. He suggested energy behaved similarly, existing only in miniature, unbreakable chunks. These fundamental, indivisible bits of energy were what he named quanta. This concept completely upended the classical belief in a seamless, continuous energy stream. Rather than flowing like a smooth river, energy moved in microscopic leaps tied directly to the radiation's frequency. To calculate the exact dimensions of these chunks, he formulated a new value, famously called Planck's constant. Though incredibly tiny, this number brought a beautiful elegance to the mathematics. The moment he applied this concept to his calculations, the results were spectacular. The dreaded infinite energy dilemma simply disappeared. His formulas finally aligned perfectly with physical reality, effectively curing the ultraviolet catastrophe. Surprisingly, Planck remained deeply skeptical of his own breakthrough. He literally referred to his fix as a mere mathematical illusion, a handy trick to force the numbers to cooperate rather than a genuine reflection of nature. He fully expected upcoming scientists to discover a more logical solution that avoided such bizarre concepts, viewing quantization as a stopgap measure rather than a universal law. He had absolutely no idea that his little mathematical hack was about to birth a completely fresh paradigm. By suggesting energy exists in distinct bundles, he accidentally built the foundation for quantum mechanics, a framework destined to dismantle classical assumptions. While history views this as a massive turning point, it barely registered as a minor footnote back then. Planck was simply trying to balance his equations, not overthrow established science. Nevertheless, his quantization concept sparked a gradual revolution that would permanently alter our grasp of matter, light, and existence. Hidden within an unassuming essay released in 1900, this modest origin story lacked any grand announcements. It simply offered a minuscule constant, a fresh perspective on energy, and a quirky solution to a stubborn puzzle. After that quiet publication, the realm of physics would never look complete in the same way again. Yet, as the new century began, most researchers felt they completely understood light. James Clerk Maxwell's brilliant equations had already proven it traveled as an electromagnetic wave, creating beautiful ripples through space. This energy perfectly demonstrated classic wave behaviors, effortlessly bending, bouncing, diffracting, and interfering. Following Planck's subtle debut of quantized energy, the scientific community fully expected the dust to settle into a comfortably modified status quo. However, a baffling new puzzle regarding light striking metal would soon stubbornly refuse to follow any established rules. This peculiar phenomenon earned the name the photoelectric effect, operating on a seemingly simple premise. Directing light at a piece of metal causes electrons to fly off its surface. Initially, this concept appeared perfectly logical, as light carries energy, and that energy simply knocks the particles loose. Based on classical wave principles, researchers assumed that turning up the light's intensity would pump more energy into the metal, meaning a brighter beam would vibrate the electrons free much faster. Yet, laboratory tests revealed a truly bizarre reality, showing that simply making the illumination stronger did not give the escaping electrons any extra kick. Instead, the crucial factor turned out to be the light's frequency. If the beam fell below a specific vibrational rate, absolutely zero particles would be dislodged, no matter how blindingly intense the glow was. Conversely, crossing that exact frequency line allowed even the faintest glimmer to effortlessly pop electrons away. This rigid cutoff completely shattered classical wave predictions, escalating a minor glitch into a massive scientific enigma. To resolve this massive scientific enigma, Albert Einstein stepped onto the stage. In 1905, famously remembered as his miracle year, he released a groundbreaking paper that completely redefined our understanding of the photoelectric effect. His hypothesis was incredibly daring. He asked whether light might actually function as a particle, a minuscule packet of energy moving in a direct path, rather than exclusively acting as a wave. Einstein proposed that illumination consists of distinct energy chunks he termed quanta of light, which we now call photons. The frequency of the light dictates the exact energy payload carried by every single photon. When a photon possesses sufficient energy, it successfully strikes an electron free from a metallic surface. However, if that energy threshold isn't met, the electron stays put, regardless of how intensely bright the light is or how many photons are fired. Think of it like trying to unlock a door with a massive ring of incorrect keys. Having thousands won't help if not a single one fits. While this concept expanded directly upon Max Planck's previous discoveries, Einstein took a massive leap forward. Instead of treating energy chunks as a mere mathematical convenience, he argued that light is physically constructed from these discrete packets. This literal interpretation was a radical assertion that faced heavy skepticism. Numerous scientists stubbornly defended the traditional wave model, pointing out that light obviously bends around obstacles and generates interference patterns just like a wave. So, how could a stream of particles simultaneously display wave-like traits? Instead of dismissing wave characteristics, Einstein introduced an even more bizarre concept: wave-particle duality. He declared that light embodies both forms, shifting between particle and wave behavior based entirely on the method of observation. This isn't an optical illusion, but a core feature of reality. Picture a sunbeam shining through a glass pane, rippling and scattering off dust particles like a fluid wave. Yet, if you magnify the scene immensely, you would witness individual energy quanta, governed by their specific frequencies, smashing into atoms and altering the physical world through discrete impacts. Wave-particle duality remains one of the most baffling concepts in science, primarily because it shatters our fundamental categories for understanding the universe. Classical physics demands that an entity must be strictly a wave or strictly a particle, never a situational hybrid of the two. The quantum realm, however, operates without regard for human logic. Einstein's photon theory aligned flawlessly with laboratory data. By tying photon energy directly to frequency, just as Planck theorized, he perfectly clarified why extremely bright, low-frequency light fails to dislodge electrons. The individual packets simply lack the necessary force. The ramifications of this breakthrough were monumental. In fact, when Einstein was awarded the 1921 Nobel Prize in Physics, It was specifically for solving the photoelectric effect, rather than for his famous theory of relativity. Despite pioneering this field, Einstein eventually grew uneasy with the bizarre quantum reality he helped uncover. He strongly opposed the probability-based theories that emerged later, famously insisting that God does not play dice with the cosmos. Yet, regardless of his personal feelings, the fundamental laws of nature were permanently rewritten. At the core of this scientific revolution was a profound mystery. Light, the very substance that lets us see, completely defies simple classification. It arrives in discrete chunks, flows in wave patterns, and strikes with particle force, constantly shifting between states to keep scientists perpetually guessing. A basic laboratory test involving metal and illumination ultimately fractured the bedrock of classical physics. After all, if light can simultaneously exist as a spread-out wave and a localized particle, what other rule-breaking phenomena might be hiding in the deepest shadows of the cosmos? To find out, we don't need to peer into the deep cosmos. We just need to look at a table. Picture a basic setup: a flashlight at one end, a piece of cardboard with 2 tiny slits, and a blank screen behind it. You shine the light and watch the projection, which sounds incredibly boring. Yet, hidden within this modest arrangement lies arguably the most mind-bending demonstration in all of science. The double-slit experiment is an absolute legend in physics. Its fame doesn't come from complex machinery. Actually, the setup is almost embarrassingly simple. However, the secrets it uncovers are profoundly complex. Some researchers even joke that this is the most theatrical scientific demonstration ever conceived, starring nothing but a flashlight and 2 cardboard cutouts. Let us first look at what classical physics tells us to expect. Think about a wave, such as sound or water, which naturally expands and interacts with itself. Picture ocean swells rolling through a pair of gaps in a seawall. As they pass through, the ripples overlap on the far side, creating a distinct layout of peaks and valleys that either amplify or neutralize one another. We call this interference, and it is a completely predictable phenomenon. Now, swap the water for physical objects. Imagine shooting tiny rubber balls at a barrier with the same 2 gaps. A few will bounce through the left opening, while others pass through the right. They never overlap. Consequently, the back screen would simply display 2 distinct clusters of marks directly behind the openings. This represents standard particle behavior, completely logical and unsurprising. So, what actually occurs when we run this test using light? When early researchers first beamed light through the dual slits, they anticipated wave-like behavior, and that is exactly what they got. The illumination fanned out and generated a classic interference layout, appearing as alternating stripes of light and shadow on the back screen. Everything made perfect sense. Just as Maxwell had theorized, light was acting exactly like a wave, but then the narrative took a bizarre turn. By utilizing delicate instruments, scientists dimmed the light source drastically, reducing the output until it emitted just a single photon at any given moment. Rather than a continuous beam, individual light particles traveled toward the cardboard barrier one by one. Logically, you would assume these isolated photons would act like physical objects, choosing either the left or the right gap. If you let the experiment run long enough, the screen should eventually display 2 distinct bright patches, mirroring the rubber ball scenario. However, reality had a different plan. Despite traveling individually, the singled photons slowly accumulated to form the exact same interference stripes. This specific layout absolutely requires waves to interact with one another. How could an isolated photon interfere with itself? Did it somehow pass through both gaps simultaneously? Was it functioning as a wave and a particle at the exact same moment? This was no trick of the light. The striped pattern remained, implying that every individual photon traveled through both openings at once, acting like a phantom version of itself, exploring every conceivable route before hitting the screen. If that revelation was not baffling enough, the plot thickened. Researchers decided to investigate by attaching detectors right at the slits to track the exact route each photon took. They figured they could simply watch the process and solve the puzzle permanently. Did the light particle choose the left gap, the right gap, or both? Shockingly, the moment they checked, the interference stripes completely disappeared. The instant the monitoring equipment was activated, the wave-like behavior ceased entirely. The light reverted to acting like standard physical objects, striking the screen behind only one slit or the other. The interference was gone. It appeared as though the simple act of watching compelled the photon to pick a definitive path. It had to go left or right, eliminating any fuzzy superpositions. The universe had been caught red-handed, and it instantly corrected its behavior to appear normal. Switch the monitors off, and the stripes reappeared. Flip them back on, and they vanished once more. The consequences of this toggling effect were massive. It was not a case of the monitoring tools physically bumping into the light particles. The equipment was entirely passive. The problem was not the physical method of observation, but the simple fact that observation was happening at all. It appeared that merely possessing the information about the photon's route was sufficient to force its wave nature to collapse into a solid particle state. In a very real way, the fabric of reality cared if someone was looking at it. This was not a one-off glitch. Scientists have recreated the double-slit test endlessly, using photons, electrons, and even massive molecules composed of hundreds of atoms. The outcome never changes. When left alone, these tiny entities behave like waves. When monitored, they act like traditional particles. If this makes you feel uneasy, you are in good company. This demonstration forms the absolute core of quantum mechanics, stubbornly refusing to be explained using everyday logic. It implies that on a microscopic level, matter does not travel along fixed trajectories. Rather, it exists as a broad spectrum of probabilities, functioning as a glowing cloud of potential outcomes. It is only when a measurement occurs that this hazy cloud solidifies into a concrete reality. Various theories try to make sense of this. Some visualize the photon as a physical wave that divides and merges back together. Others rely on mathematical probabilities, treating the wave function simply as a predictive calculator. Meanwhile, supporters of the many worlds theory suggest that every single possibility splinters off into a parallel universe. Regardless of the preferred explanation, the raw data stays identical. Before we look at it, the particle simply refuses to pick a definitive form. What started as a basic check on the properties of light has evolved into a massive enigma regarding the fundamental fabric of existence. Does the act of looking actively mold the cosmos? Can raw information dictate physical existence? Is the universe inherently undecided until we force it to show its hand? These go far beyond mere philosophical musings. They are hard scientific inquiries grounded in verified testing. While the double-slit test refuses to hand us neat conclusions, it delivers one monumental realization. The cosmos is not a rigid, predictable clockwork mechanism. Instead, it is a bizarre, glowing fabric stitched together from pure potential, and it reacts in fascinating ways to our attention. Using nothing but a pair of slits, a beam of light, and a blank wall, we have learned that the universe playfully winks at us when we look away and freezes in place the moment we pay attention. Building on that idea of a universe that freezes the moment we pay attention, we need a way to describe what happens when nobody is looking. If quantum theory has a secret spell whispered through its foundation, it is undoubtedly Schrödinger's equation. Rest assured, we are not about to dive into a dry mathematics lecture. Nobody wakes excited to stare at partial differential equations. Yet, this specific formula stands apart. Rather than just a random assortment of corkboard symbols, it serves as the silent, steady pulse of the quantum realm. During the 1920s, scientists found themselves stumped by particles that refused to act like normal matter. Electrons displayed wave-like characteristics, while photons behaved like spooky, probability-driven phantoms. The classical rules of motion handed down by Isaac Newton were completely useless here. The cosmos demanded an entirely fresh vocabulary. This is where Erwin Schrödinger stepped onto the stage. In 1926, he introduced a formula capturing not merely the movement of particles, but the exact way their wave functions developed as time passed. His creation was beautifully simple, incredibly concise, and astonishingly powerful. Even if it appears to be a chaotic jumble of operators and Greek characters, the fundamental narrative it tells is straightforward. It maps out the evolution of a quantum system. Let us ignore the complex notation for a moment and focus on the true star, the wave function, typically represented by the Greek symbol psi. If that term feels too theoretical, try imagining it as a mathematical murmur, revealing every possible detail about a quantum setup. It hints at a particle's potential location, its likelihood of being found there, and its current or future momentum. Instead of providing absolute certainties, the wave function deals exclusively in odds. In the classical realm, if you picture a particle as a tiny speck traveling through space, physics draws a crisp arrow indicating its precise speed and exact coordinates. Schrödinger's framework throws that out the window. In its place, we get a fuzzy, undulating mist, a wave indicating the particle is probably in this spot, but might also be in that spot, or perhaps hovering slightly above. This is exactly where the true wonder unfolds. Schrödinger's formula allows us to watch this misty cloud develop as time ticks forward. It illustrates the transformation of the wave function as the particle travels, which really just tracks how the various positional possibilities drift and merge. The moment we actually measure the particle, the second we demand to know its exact location, the wave function instantly collapses. The fuzzy cloud vanishes in a flash, leaving behind one concrete, undeniable answer. The particle is right there, but this concrete reality only solidifies after we choose to observe it. This perspective of a wave-driven existence drastically contrasts with the clockwork universe envisioned by earlier scientists. Rather than watching matter follow strict, predictable trajectories like planets orbiting a star, we are now looking at swirling oceans of chance, brimming with vagueness, right up until an observation locks them into place. To make this easier to visualize, picture yourself standing blindfolded inside a large room. Hidden somewhere in that space is a completely silent feline. You cannot see or hear the animal, but you have a supply of small balls to throw, listening carefully for the thud when they hit the floor or the cat. As minutes pass, you begin constructing a mental image of the feline's probable location, noting zones of high likelihood and areas of low probability. That conceptual map perfectly mirrors the wave function. It does not depict the world exactly as it is, but rather as it has the potential to be. Next, imagine formulating a mathematical rule that predicts how your mental map will update as time goes by. Perhaps the feline prefers hiding in corners or lounging near heaters. That specific rule would act as your ultimate guide to predicting the cat's next likely spot. This is precisely what Schrödinger accomplished, though his focus was on electrons rather than household pets. The mathematical formula he devised is incredibly fluid and unbroken. It permits these probability waves to undulate and drift, much like ripples spreading across a calm lake, while it honors fundamental natural symmetries, such as energy conservation and time progression. It has zero interest in absolute guarantees. It outlines what is possible, never what is guaranteed. The truly captivating part is just how flawlessly this framework operates. Researchers have applied Schrödinger's formula to explain a massive variety of phenomena, ranging from atomic architecture and molecular bonding to the quirks of superconductors and semiconductors. It even forecasts bizarre occurrences like quantum tunneling, a process where particles magically pass through solid barriers they classically shouldn't be able to penetrate. The formula operates timelessly, ticking away smoothly to provide a chart of the fundamentally unknown. Perhaps its greatest triumph was decoding the hydrogen atom, the most basic atomic structure in existence. Prior to quantum mechanics, scientists were baffled as to why electrons orbiting a nucleus would settle into distinct energy levels instead of just crashing inward or floating away. Schrödinger's mathematics proved that electrons do not zip around like tiny solar system planets. Rather, they create standing waves, which are essentially stable probability formations encircling the nucleus. These formations are the atomic orbitals frequently illustrated as soft, cloudy shapes in science books. Furthermore, these cloudy illustrations are far more than just artistic metaphors. They map out the genuine, quantifiable odds of discovering an electron in a specific spot if you were to check. We are not looking at traditional orbits, we are looking at presence zones. These zones only exist because the electron is far more than a basic piece of matter. It is fundamentally a vibration within an ocean of likelihoods. While this concept is undeniably weird, it is also remarkably coherent. Unlike certain scientific models that require constant adjustments, Schrödinger's formula has matured perfectly, like a vintage wine. It simply functions. Time after time, it has forecasted the actions of the microscopic world with mind-blowing precision. Despite this, it stays incredibly intangible. A wave function is not something you can physically grasp or look at. Nevertheless, it is actively outlining the spooky potential of every single thing around you, from the atoms steeping in your morning tea to the microchips powering your smartphone. This brings us to the deep philosophical questions. What exactly is the true nature of a wave function? Does it merely represent human understanding, or is it a physical component of the universe itself? A real entity that exists right up until it collapses into a single result. Various schools of quantum thought argue passionately over this exact point. Yet, the mathematical formula remains completely neutral. It just performs its job in a quiet, dependable, and deeply odd manner. Interestingly, Erwin Schrödinger harbored his own reservations about his creation. Although he took immense pride in his mathematical breakthrough, he was deeply uncomfortable with the notion that matter lacked fixed characteristics prior to being measured. His legendary thought experiment featuring a feline that is simultaneously deceased and alive was actually designed as a protest against the very ambiguity his own research had introduced. He provided the mathematical framework for quantum waves, only to spend his later years questioning the fundamental meaning of those waves. Regardless of his personal doubts, it is impossible not to marvel at his monumental achievement. In a reality that constantly pushes for absolute black and white answers, Schrödinger provided a much softer alternative, a glowing realm of possibilities, a gentle mathematical compass pointing toward what might occur. His formula never yells or dictates, it simply proposes and flows. Through this elegant motion, it uncovers a cosmos that is much more hushed, nuanced, and enigmatic than humanity ever dared to dream. Down at the most microscopic levels, movement isn't always straightforward movement, and location isn't always a fixed point. Absolute certainty becomes a rare privilege rather than a basic rule. Yet, thanks to one beautifully crafted equation, we are still able to navigate our way softly, and mathematically right through the mist. Navigating through that mathematical mist brings us face to face with a stark contrast between everyday reality and the macroscopic realm. In the macroscopic universe, the domain of bowling balls, bicycles, and apples determining an object's exact location and simultaneous speed is trivial. Think about driving. A GPS pinpoints your coordinates while a radar gun tracks your velocity. There is zero conflict. However, the subatomic realm shatters these intuitive rules. Back in the 1920s, Werner Heisenberg unveiled a concept so profoundly bizarre, yet so foundational to quantum mechanics, that it continues to make seasoned physicists and fresh students pause. This is the uncertainty principle. At its core, it reveals that the foundation of existence imposes strict boundaries on human knowledge. Specifically, the rule dictates an inverse relationship. The more accurately you pin down a particle's location, the fuzzier its momentum becomes, and vice versa. Remember, momentum simply is mass multiplied by velocity, quantifying overall motion. Applied to daily life, this idea seems ridiculous. Why would identifying an object's location obscure its speed? Watching a train arrive at a platform lets you effortlessly gauge both its whereabouts and pace. Yet, nature forbids such dual clarity at the microscopic level. Crucially, this limitation has nothing to do with clumsy equipment or primitive technology. We aren't just waiting for better sensors. This fundamental blurriness is permanently stitched into the tapestry of the cosmos, independent of our measuring devices. Picture yourself attempting to track a single electron to determine its speed and location. Your instinct might be to illuminate it with light. However, light consists of energy-carrying packets called photons. The moment a photon collides with your target electron, it alters the electron's trajectory. Imagine trying to locate a fragile soap bubble in a pitch-black room by hurling tennis balls into the darkness. You will certainly locate the bubble, but you will obliterate it simultaneously. Nevertheless, Heisenberg wasn't merely highlighting physical disturbance. His revelation is deeply embedded within the mathematics governing quantum theory. Even if you possessed a ghost-like method to observe the electron without bumping into it, the inherent ambiguity would persist. Far from being a flaw, this ambiguity is a fundamental feature. The true root lies in the fact that particles behave like waves. Think about pinpointing the exact location of an ocean wave. You might identify the crest, but the wave extends broadly across the water. Similarly, an electron is represented by a wave function, a dispersed cloud of potential locations. When this wave is broad, the particle's whereabouts are hidden, though its momentum can be calculated accurately. Conversely, if you compress the wave to isolate a precise location, the momentum becomes unpredictable, turning the wave jagged. This represents an inescapable cosmic compromise. Mathematically, multiplying the uncertainty of momentum by the uncertainty of position always equals or exceeds a sinuscule value. Planck's constant divided by 4 pi. Because this threshold is so tiny, the effect is unnoticeable in our macroscopic lives. You could track a flying baseball's velocity and coordinates with astonishing exactness without brushing against quantum boundaries. However, when you zoom in on atoms and electrons, this blurriness dominates, fundamentally dictating the behavior of the unseen world. Should you attempt to confine a particle within a microscopic box to lock in its coordinates, it reacts with frantic energy. Its momentum skyrockets into extreme uncertainty, causing it to dart around erratically. The harder you restrict its location, the more violently it fights back, as if the universe despises absolute spatial precision. This isn't a glitch, it is an unerasable smudge on reality. A helpful metaphor is attempting to grasp fog in your palms. Squeezing tightly causes the moisture to slip away, whereas relaxing your grip allows more mist to remain. This captures the fragile equilibrium between acquiring specific knowledge and sacrificing another piece of information. Philosophically, this concept acts as a caution sign for the quantum realm. It demonstrates that the limits of understanding stem from the architecture of existence rather than human shortcomings. We aren't watching miniature billiard balls bounce around. We are observing fluid waves and probabilities that reject strict confinement. Furthermore, this rule is why atoms maintain their structure. You might ask why negatively charged electrons don't crash into the positively charged nucleus, given that opposite charges attract. The answer is that the uncertainty principle forbids electrons from resting still. If an electron plummeted into the nucleus and stayed, its location would be known perfectly. Consequently, its momentum would spiral into infinite uncertainty, demanding infinite energy, a scenario nature prohibits. Therefore, electrons hover because quantum mechanics physically prevents total collapse, providing a natural cushion. This restriction extends beyond position and momentum, applying equally to paired properties like time and energy, or orientation and angular momentum. In every pairing, sharpening focus on one variable forces you to blur the other, a universal microscopic law. Surprisingly, there is a reassuring quality to this. This uncertainty isn't mere chaos. Instead, it operates as an elegant fuzziness, a structured ambiguity providing the cosmos with rich texture. This blurriness permits chemistry to function, keeps atoms stable, and enables particles to tunnel through barriers. Stripped of this flexibility, the universe would be far too rigid to support life. Historically, science has focused on measuring, predicting, and achieving absolute certainty. Heisenberg inverted this ambition, proving that certain facets of nature will forever remain just beyond our grasp. This isn't a scientific defeat, it is simply reality. Oddly enough, the uncertainty principle encourages us to embrace the unknown. It asks us to rest comfortably within the blur and admire the softness hidden beneath the surface. It reminds us that the deepest truths of our universe aren't sharp, but rather unresolved, rippling and cloudy. And perhaps that is precisely what makes them so beautiful. Building on that beauty, we now step into a realm where the very nature of existence becomes wonderfully blurred. In our daily lives, we expect objects to commit to a single condition. A tossed coin resolves into either heads or tails. A light switch rests firmly in the on or off position. Even your tears are distinctly hot or cold, even if they occasionally settle into a questionable lukewarm middle ground. However, this neat categorization completely shatters when we zoom into the quantum realm. At the microscopic level, particles refuse to simply pick a lane. Instead, they linger in a bizarre middle ground, blending every potential outcome together. Welcome to the fascinating domain of quantum superposition. To grasp this concept, let us return to the idea of flipping a coin. Under the rules of classical physics, a coin soaring through the air follows a definite, predictable path. Even if the final result remains a mystery to you until it hits the ground, the coin is definitively heads or tails during its entire flight. The outcome is merely hidden from your view. Quantum mechanics throws this logic out the window. If you were to toss a quantum coin, it would not secretly commit to a side while your back is turned. Rather, it slips into superposition, embodying a mathematically weighted mixture of heads and tails simultaneously. It is not merely undecided, nor is it rapidly flipping back and forth between the two options. It physically occupies both states at the exact same time, right up until the moment you check. The instant you observe the system, this superposition shatters. Your quantum coin finally commits to a single face, making your measurement a concrete reality. Yet, prior to your glance, it was not just a hidden answer, it was genuinely both. Accepting this reality is incredibly difficult, going far beyond mere counterintuition. into the territory of profound weirdness. Originally, scientists introduced superposition to explain how quantum entities, such as photons and electrons, behave. Instead of traveling along set trajectories, these tiny particles exist as wave functions, which are essentially mathematical formulas mapping out probabilities. Every conceivable outcome, whether an electron's spin points up or down, or a photon veers left or right, is baked into this equation. All these potential realities survive together until an observation forces a single result. You can visualize this as a misty, fog-covered landscape of potential destinations. The particle is not strolling down a single defined trail. Instead, it is smeared across every conceivable path it might travel. The moment you interact with it, this hazy fog instantly crystallizes into one exact spot, much like a sudden flash of lightning, illuminating a single peak through the mist. This mind-bending principle birthed arguably the most legendary thought experiment in the history of physics, Schrödinger's cat. Imagine locking a feline inside a closed container alongside a radioactive atom, a monitoring device, and a flask of lethal poison. Should the atom undergo radioactive decay, the sensor triggers, shattering the flask and killing the cat. If the atom remains stable, the feline survives. According to quantum theory, before anyone checks the atom, it rests in a superposition of both decayed and undecayed conditions. Consequently, the cat must also be simultaneously alive and dead until a person finally opens the container. Erwin Schrödinger never intended for this scenario to be taken as literal fact. He designed it to expose the sheer ridiculousness of scaling quantum mechanics up to everyday macroscopic objects. Nevertheless, the concept resonated deeply, transforming superposition from a purely mathematical abstraction into a profound statement about the bizarre nature of reality itself. Despite its inherent strangeness, superposition is far from a theoretical glitch or an awkward loophole that scientists simply put up with. It stands as one of the most potent pillars of quantum mechanics, serving as the foundation for a massive chunk of modern quantum technology. Consider the realm of quantum computing. Traditional computers rely on bits as their fundamental data units, restricted to being either a 0 or a 1. Every single function your laptop or smartphone performs, from streaming songs and displaying photos to sending texts, relies on combining these two basic states. Quantum machines, however, operate using qubits. Unlike standard bits, a qubit can occupy a superposition of 0 and 1 concurrently. It is not rapidly toggling between the two values. It is authentically blended into both. Consequently, a lone qubit stores vastly more data than a traditional bit. When you link multiple qubits together through entanglement, they can embody an astronomical number of states all at once. This capability empowers quantum computers to tackle specific mathematical challenges with an efficiency that classical machines could never dream of matching. This is not sorcery. It is simply mathematics obeying quantum laws. Incredibly complex challenges, such as modeling intricate molecular structures or streamlining massive logistical networks, suddenly become solvable, all thanks to the superposition of qubits. We also see superposition at work in quantum cryptography, where it guarantees that any attempt to eavesdrop on data will immediately be detected. Furthermore, in the field of quantum sensing, this principle enables researchers to pick up on minuscule fluctuations in gravitational and magnetic fields. These applications are not distant science fiction fantasies. They are tangible technologies currently in active development. However, there is a major catch. Superposition is incredibly fragile. Quantum setups are notoriously sensitive to disruption. The tiniest environmental interference, whether from rogue photons, subtle vibrations, or even wandering air molecules, can instantly destroy the wave function. We call this collapse decoherence, and it remains one of the most formidable hurdles in engineering reliable quantum devices. Imagine attempting to balance a delicate feather on a pencil point while a person in the adjacent room continuously sneezes. The superposition evaporates the very second the system brushes against the external environment. Yet this extreme sensitivity is exactly what makes quantum mechanics so captivating. These systems provide immense computational power, but only when kept in strictly controlled, perfectly isolated environments. They grant us a window into probabilities rather than absolute guarantees, forcing us to completely redefine what it means for something to simply exist. This realization naturally sparks a profound philosophical debate. When particles occupy multiple states at once, are we looking at the true fabric of reality, or merely a mirror of our own limited understanding? Certain interpretations argue that the wave function simply maps our knowledge, acting as an educated prediction until a measurement occurs. Alternative viewpoints insist the wave function is a tangible physical entity, meaning the particle authentically inhabits multiple states until forced to commit. Regardless of which camp you side with, quantum superposition demands that we release our strict adherence to classical logic. It reveals a universe where contradictions happily coexist, where a system can simultaneously be this and that, here and there, yes and no. At its fundamental level, reality is not a single, straightforward string, but a rich, overlapping tapestry of unresolved potentials, waiting for an observation to pull a single thread free. It is undeniably weird and occasionally unsettling, yet undeniably gorgeous. Through the bizarre lens of superposition, we discover a cosmos that is fluid rather than stiff, poetic rather than purely mechanical. It is a reality that embraces uncertainty and contradiction not as errors, but as essential characteristics. Ultimately, this mindset unlocks revolutionary methods to calculate, connect, investigate, and dream about the endless possibilities that emerge when the universe simply refuses to make up its mind. Building on those endless possibilities, let us explore a concept that takes connection to a whole new level. Picture a pair of winter gloves, one designed for the left hand and the other for the right. If you seal them in separate packages and mail one across the globe, you remain ignorant of which box holds which glove. However, the second you tear open your package and discover the left glove, you immediately understand the distant is meant for the right hand. There is zero magic here, just basic deduction, because the gloves were permanently assigned their roles from the very beginning. Quantum entanglement, however, throws this everyday logic completely out the window. Instead of pre-assigned roles, imagine a pair of magical gloves that remain totally undecided about their handedness until you actually look at one. The instant you check your box, the glove inside picks a side, and its distant partner immediately adopts the opposite orientation, regardless of the physical gap between them. This goes beyond simple correlation. The actual traits of these particles simply do not exist prior to observation. The very act of checking one particle forces the other into a definite state. Welcome to quantum entanglement, easily one of the most mind-bending and bizarre aspects of the subatomic realm. To understand the mechanics, consider what happens when two particles cross paths. Whether they are born from the same event, smash into each other, or simply interact in specific ways, they can become deeply linked. This linkage means their quantum identities fuse together. Consequently, any action impacting one particle genuinely influences its partner, even if they are separated by massive cosmic distances. Think about generating a pair of entangled light particles, or photons, whose polarization directions remain totally undefined. Eventually, one might be measured as vibrating vertically, while the other vibrates horizontally. Crucially, they never pre-plan this division. Instead, they exist in a blended, shared state of pure potential, encompassing every possible outcome simultaneously. The reality only solidifies the exact second you observe the first photon. In that identical fraction of a second, the second photon's state also locks into place. There is zero travel time, zero transmission of a signal, and zero opportunity for them to confer. If you check a photon in Paris, its entangled twin sitting in Tokyo will instantly align its behavior, as if the cosmos just refreshed both files at the exact same millisecond. Albert Einstein famously dubbed this bizarre phenomenon spooky action at a distance. Naturally, Einstein was not a fan of anything spooky. He was a staunch defender of locality, a core principle of his theory of relativity, stating that an event in one spot cannot immediately influence an object far away. According to this rule, absolutely nothing, not even pure data, can outpace the speed of light. The notion that two tiny specks of matter could perfectly synchronize their behaviors without sending a physical signal made him incredibly uneasy. Consequently, in 1935, Einstein teamed up with Boris Podolsky and Nathan Rosen to release a famous paper questioning whether quantum mechanics was actually a complete theory. They suggested that if the universe permitted such instantaneous links, the current mathematical framework must be overlooking a crucial piece of the puzzle. They proposed the existence of hidden variables, secret underlying instructions dictating the results from the very beginning. In Einstein's view, reality had to be organized, predictable, and above all, strictly local. However, as the decades rolled on, laboratory tests started validating the bizarre predictions of quantum theory. Entanglement was proven to be a genuine feature of nature, and those theoretical hidden variables completely failed to materialize. During the 1960s, a physicist named John Bell formulated a brilliant mathematical test, now celebrated as Bell's theorem. This inequality provided a concrete way to differentiate between standard quantum forecasts and theories relying on hidden variables. When researchers ran these tests repeatedly in the lab, quantum mechanics emerged victorious every single time. The behavior of entangled particles simply cannot be replicated by any local hidden instructions. The measurement outcomes appear completely random on their own, yet they match up with flawless precision. It is almost as if the two particles are reading from a secret, invisible script that only gets written at the exact moment the performance begins, allowing them to improvise in perfect, eerie harmony. Despite this instantaneous link, you cannot exploit entanglement to transmit data faster than the speed of light. Doing so would shatter the laws of cause and effect. But fortunately, the laws of physics block this loophole. Even though the particles react to each other without any time delay, the specific results of your measurements are entirely left to chance. Because you cannot force your particle to yield a specific result, you cannot use it to spell out a message. The instantaneous bond is undeniably real, yet it remains utterly useless for sending communications. Picture two individuals tossing coins on completely opposite ends of the galaxy. Every single toss yields a random result, but miraculously, whenever the first person gets heads, the second person is guaranteed to get tails. Neither coin flipper can predict their own outcome beforehand. They are not secretly texting each other. They are simply locked in a synchronization that completely ignores physical space. The most astonishing detail is that this profound bond never degrades, no matter how far apart the particles drift. You could pull two entangled entities apart by the width of a room, across an entire continent, or even across a light year, and their quantum link would stay perfectly intact. Science has yet to discover a maximum range for this effect. In fact, scientists have successfully entangled particles across hundreds of kilometers using orbiting satellites, with the data continuously backing up quantum predictions. But what actually is this phenomenon? Is it an unseen cosmic tether? A unified identity stretched across the void? Or perhaps a delicate smear of data bridging the gap between particles? Honestly, the scientific community does not have a definitive answer. Various interpretations of quantum mechanics provide entirely different explanations. Certain physicists view entanglement purely as a measure of our knowledge about a system, rather than a physical property of the system itself. Conversely, others interpret it as proof that reality is woven from a profoundly non-local fabric. Taking it a step further, some theorists argue that entanglement is far more than just a weird subatomic parlor trick. It might be the actual foundation of space and time. Certain researchers suggest that space-time, the literal geometric structure of our cosmos, could actually be generated by vast, complex webs of entanglement connecting microscopic quantum bits. If this hypothesis holds water, entanglement does not merely occur within the boundaries of space. It is the very glue that constructs space in the first place. While this remains a daring and heavily researched concept, it underscores how deeply vital entanglement might be to the fundamental architecture of existence, rather than just a quirk of particle physics. Just like numerous other quantum concepts, this isn't merely abstract philosophy. It has incredibly tangible real-world uses. Entanglement serves as the absolute bedrock for quantum teleportation. We aren't talking about beaming people across the galaxy like in Star Trek, but rather the genuine transfer of delicate quantum states from one location to another. Furthermore, it is the driving force behind quantum key distribution, an ultra-secure communication technique that ensures absolute privacy. Should an eavesdropper attempt to intercept the encryption key, the delicate entangled state is disturbed, instantly alerting the users to the interference. Within the realm of quantum computing, entanglement enables highly intricate calculations across multiple qubits, achieving feats that cannot be broken down into basic individual steps. This deep interconnection provides quantum machines with their immense processing advantage, offering a type of massive parallelism that ordinary computers simply cannot match. Consequently, this spooky action that once caused Einstein so much philosophical distress has transformed into the bedrock of cutting-edge technology. Even though he despised the concept, the mathematical elegance of entanglement is undeniable. Although the grand unification of relativity and quantum mechanics remains an unsolved puzzle, both frameworks continue to achieve miraculous success within their specific domains. Ultimately, entanglement teaches us that the cosmos is not just a random assortment of isolated objects bouncing around. Instead, it is a profoundly linked web where widely separated pieces can still belong to a single unified whole. It reveals that total separateness is sometimes just an illusion. Naturally, we don't experience this in our everyday routines. You never wake up quantumly entangled with your neighbor, nor does your morning coffee magically reflect the state of a stranger's spoon. Yet, down at the most microscopic scales, this silent partnership between particles is continuously humming away everywhere all the time. Perhaps that is the most beautiful takeaway of all. Even within a colossal universe filled with silent stars and unimaginable distances, there are still profound echoes of togetherness, acting instantly, invisibly, and unshakably real. While those invisible cosmic connections bind the universe together, there is another famous quantum concept that brings things much closer to home. In fact, it brings them right into a cardboard box. You have likely heard of Schrödinger's cat, arguably the most famous animal in the entire history of science. This curious feline serves as the unofficial emblem for quantum physics, forever trapped inside a mental exercise so bizarre that people frequently mistake it for a joke. Honestly, it kind of is a joke. Erwin Schrödinger never intended for anyone to take it literally. Yet, just like any brilliant metaphor, it highlights a profound unease sitting right at the core of quantum mechanics. To understand why, we need to travel back to the 1930s. During this era, scientists were struggling to figure out the actual meaning behind quantum theory. Their mathematics was flawless, and their predictions were incredibly precise. However, the physical implications remained a mystery. They debated whether the wave function was a tangible reality or merely a mathematical trick. Did tiny particles genuinely occupy multiple states at once before someone measured them? Erwin Schrödinger, who had already achieved fame for his beautiful quantum equation, harbored deep doubts about this. He was highly skeptical of his colleagues who wanted to stretch the concept of superposition to its absolute limits, particularly regarding the act of measurement. To him, applying the bizarre rules of electrons to everyday macroscopic items, like a household pet, felt completely wrong. To illustrate his point, he invented a darkly playful scenario. He asked what would happen if we took the strange rules of the subatomic realm and magnified them to the size of something you could actually cuddle. Picture a completely sealed container. Inside this container sits a cat. Sharing the space with the feline is a single radioactive atom, a Geiger counter, a small glass vial filled with toxic gas, and a mechanical trigger. The setup is simple but deadly. If the radioactive atom happens to decay, an event that quantum mechanics dictates is entirely random. The Geiger counter will detect the radiation. This detection activates the trigger, which shatters the glass vial, releasing the poison and tragically ending the cat's life. But here is where the bizarre twist comes in. According to quantum rules, until someone actually looks at the atom, it remains in a superposition, meaning it has both decayed and not decayed at the exact same time. Consequently, the entire apparatus, the sensor, the toxic gas, and the cat itself, must also enter a state of superposition. This implies the feline is simultaneously alive and dead. We are not speaking figuratively here. Under certain interpretations, this is meant literally. Naturally, nobody ever actually locked a pet inside a quantum chamber. Schrödinger was simply illustrating a philosophical argument. He thought it was utterly ridiculous to imagine a warm, whiskered creature that loves taking naps existing in such a fuzzy, undefined condition. To him, it was not just weird, it was complete nonsense. Despite his intentions, the concept became legendary because it perfectly encapsulated quantum indeterminacy in one striking mental picture. A feline that is simultaneously living and deceased until someone lifts the lid. This provides a brilliant way to visualize an unmeasured system. It is not about being undecided, it is about pure potential. Before its observation forces the wave function to collapse, the setup holds every single possible outcome, every future and every state all at once. Ultimately, this thought experiment is not actually about animals. It is about the limits of what we can claim about reality before we actually look at it. In the quantum realm, the act of observing is incredibly important. Prior to measurement, any system exists as a hazy cloud of probabilities, with every potential outcome woven into the wave function. However, the second you interact with that system to gather data, the cloud instantly collapses. The system chooses a single state, making one possibility real while erasing all the others. This brings up a massive complication. What actually qualifies as a measurement? Does it require a conscious mind, a piece of machinery, or just a bump from the surrounding environment? Various theories offer different explanations, and this ongoing debate is exactly why the feline remains so popular. It highlights a glaring issue. While quantum math is amazingly good at predicting results, it completely fails to explain what is actually going on behind the scenes. Some scientists favor the Copenhagen interpretation, which basically tells you to stop overthinking it. They argue the wave function provides all the knowledge we can possibly have, and measuring it simply uncovers what was already waiting there. On the other hand, fans of the many worlds interpretation suggest the feline is both living and deceased in completely different, branching realities. In this view, opening the container does not collapse anything. It just determines which universe you happen to be experiencing. Then there is the decoherence perspective, which claims that interacting with the surrounding environment naturally washes away superpositions, making things look normal and classical. Under this framework, the pet never actually sits in a weird limbo. Instead, it becomes so deeply entangled with countless environmental factors that we simply lose the ability to track the quantum effects. The superposition does not disappear. It just becomes impossible for us to access. Every single one of these viewpoints brings its own philosophical complications. However, they all share one fundamental agreement. Quantum entities do not act like tiny versions of everyday objects. They do not just sit quietly waiting for us to find them. Instead, they change and evolve through complex, probability-driven processes that defy common sense. So, how does this affect our imaginary pet? It means the container is much more than just a physical barrier. It represents the dividing line between the classical reality we know and the bizarre quantum realm. It is a theater where the laws of nature bend into strange shapes, making simple questions like, is the pet breathing? Impossible to answer directly. We are forced to accept that the creature exists in a blended state of living and deceased, until we lift the lid and force that ambiguity to resolve into a single fact. This makes the feline the ultimate symbol for unmeasured quantum setups. Down at the microscopic level, things change and move based on the Schrödinger equation, but this mathematical evolution does not choose a single direction. It explores every conceivable route simultaneously. An electron does not just fly from one spot to another, smears out across every possible path and detour until an observation forces it to pick a single location. The pet in the container is simply a large-scale illustration of this exact same behavior. The only difference is the size, not the underlying rules. And that exact realization is what bothered Erwin Schrödinger so much. If these rules genuinely apply to all matter, then, on some fundamental level, everything, including human beings, must be caught in a superposition. This leaves us with a slightly creepy final thought. What happens if the person doing the observing is also part of the quantum system? If lifting the lid forces the pet's wave function to collapse, what exactly is collapsing our own wave function? Where do we draw the line between the observer and the observed? Are we just another domino in a massive quantum chain, forcing probabilities to collapse wherever we step? Or are we simply gliding along the wave, surfing through a sea of probabilities without knowing where the next collapse will drop us? Ultimately, this famous thought experiment goes far beyond life and death. It explores the nature of human knowledge and the bizarre relationship between what is real and what is observed. It questions what it even means to declare a fact when the simple act of declaring it alters the result. It serves as a lasting reminder that in the quantum realm, absolute certainty is incredibly scarce. Clarity always comes with conditions, and sometimes the universe is just waiting for us to open the box and take a peek. Building on that idea of peeking into the unknown, let's examine how physical barriers behave when we zoom in. In daily life, solid obstacles are reliable. Toss a tennis ball against a wall without enough force and it bounces back. The universe rejects your attempt and the ball faithfully follows classical mechanics. However, step into the microscopic domain and that reliability vanishes. A subatomic particle can strike a barrier, lack the energy to cross it, and somehow materialize on the opposite side. There is no shattering, cracking, or squeezing through gaps. The particle simply acts as though the obstruction was an illusion. Scientists call this quantum tunneling. It is a mind-bending effect that makes you question if the cosmos is playing a joke. Yet, this process is genuine, measurable, predictable, and essential to the universe. Ultimately, the secret is pure probability. To grasp how tunneling operates, we must revisit wave functions. In quantum mechanics, entities like electrons are not merely tiny spheres zipping through space. They are defined by wave functions, mapping out a cloud of potential locations. These probability waves stretch through space, slowly diminishing rather than stopping abruptly. Consequently, even when a particle faces a restricted area it lacks the energy to access, its wave function can still bleed slightly into that forbidden territory. Picture a particle moving toward an energy barrier taller than its own energy level. Classically, this results in an immediate rebound, but a quantum wave function refuses to disappear at the obstacle. Instead, it gradually fades, like a muffled voice echoing through a thick wall. Provided the barrier is sufficiently thin and not overwhelmingly high, that faint shadow can reach the far side. Though the particle lacks the physical energy to vault over the top, its probability wave can tunnel straight through. Once a fraction of that wave function penetrates the barrier, a small but real mathematical chance exists for the actual particle to instantly manifest on the other side. This is not sorcery, it is simply mathematics. While theoretical, this concept drives tangible processes, particularly in atomic structures. Consider radioactive decay. Certain unstable atomic nuclei seek stability by ejecting alpha particles consisting of 2 protons and 2 neutrons. A massive nuclear force traps these particles deep inside the nucleus. Based on traditional physics, they lack the energy to break free, yet they escape constantly. Quantum tunneling explains this. Inside the core, the alpha particle's wave function extends to the boundary of the nuclear barrier. Despite low odds, a continuous opportunity exists to tunnel outward. Over time, those minuscule probabilities accumulate until the particle bursts free. Without tunneling, numerous elements would remain perfectly stable forever, and nuclear physics would essentially cease to function. Furthermore, this phenomenon is the vital ingredient for nuclear fusion. Deep within stellar cores, extreme heat and pressure force hydrogen nuclei tightly together. However, even under such brutal conditions, these nuclei lack the raw energy to defeat the electrostatic repulsion, pushing their positive protons apart. Relying solely on classical math, stellar fusion would occur far too rarely. Nevertheless, stars burn brightly because of tunneling. Driven by intense heat, hydrogen nuclei approach closely enough that their probability waves intersect. A minuscule fraction will successfully tunnel past the repulsive force and merge. Multiply that microscopic probability by the astronomical quantity of atoms inside a star, and the result is a continuous fusion reaction. This is the engine generating everything from sunshine to supernovas. We also harness tunneling in terrestrial labs, factories, and computing research. A perfect illustration is the Scanning Tunneling Microscope, or STM. This instrument enables researchers to observe surfaces down to single atoms. It works by positioning an ultra-sharp metallic tip incredibly close to a target material, leaving a gap of just a few nanometers. Across this void, electrons naturally tunnel between the surface and the tip. By tracking this tunneling current, the device constructs a highly precise topographical map of the atomic landscape. Amazingly, the STM never makes physical contact with the atoms. The imaging depends exclusively on tunneling, capitalizing on the electron's ability to silently glide through empty space. This non-contact technique grants scientists a stunningly precise window into the quantum terrain. Additionally, tunneling forms the foundation for specific electronic parts, like quantum dots and tunneled diodes. It is also a major factor in the future of computing. As engineers shrink transistors to microscopic dimensions, they collide with quantum boundaries. At the nanometer scale, electrons begin tunneling through insulating layers previously thought to be solid. It is as if the walls inside our microchips are allowing particles to sneak through. This introduces both hurdles and possibilities. Traditionally, it generates unwanted noise and erratic behavior in standard circuits. Conversely, it opens the door to innovative quantum technologies designed to exploit tunneling rather than fight it. Ultimately, quantum tunneling offers a profound lesson about reality. We typically perceive our environment as a collection of rigid borders, but the subatomic realm is far more nuanced. Obstacles are never truly impassable. They are probabilistic suggestions rather than absolute laws. While this might feel unsettling, it possesses a strange elegance. Thanks to tunneling, particles are not confined to the straightforward paths we imagine. They can cheat, slip, and blur through the cracks of logic. This reminds us the universe is not a machine of perfect gears, but a shimmering tapestry of possibilities. Your tennis ball will always bounce off a wall, but an electron, a photon, or an alpha particle might just glance at that same barrier and take the shortcut. And remarkably, nature lets them. Building on that mind-bending reality, we have to rethink our most basic assumptions about empty space. When we go about our daily routines, the concept of nothing is pretty straightforward. We imagine a completely blank page, a totally empty room, or that mysterious void beneath your bed that constantly swallows your socks. If we carry this everyday logic over into traditional physics, we tend to visualize the cosmic vacuum as a flawless, freezing, and utterly silent emptiness. However, the quantum realm completely shatters this illusion. In this microscopic world, a true void simply does not exist. Instead, the quantum vacuum acts as a buzzing, hyperactive theater. You won't find any sound, light, or ordinary atoms in it, yet it is anything but bare. Even if you were to extract every single particle and quiet every active field, this void would still boil with raw energy. Down at the most fundamental levels, the fabric of space pulses with unseen motion. You have waves cresting and crashing, alongside tiny particles that pop into reality and instantly evaporate. Think of it as a faint buzzing hidden inside total quiet, or a subtle illumination lurking behind pitch blackness. This relentless motion all traces back to the rules of uncertainty. Werner Heisenberg's famous principle isn't just restricted to measuring a particle's momentum and location. It equally governs the relationship between time and energy. Consequently, even inside a completely empty zone, where energy levels ought to be exactly zero, temporary energy spikes are allowed to occur. These sudden jolts birth what we call virtual particles. They materialize out of nowhere, linger for an unimaginably brief fraction of a second, and then dissolve back into the void. We label them virtual, not to suggest they are fake, but simply because our instruments cannot capture them directly. We can only prove they are there by looking at the physical impacts they leave behind. While these fleeting quantum ghosts might sound like a quirky math trick, they actually drive very real physical outcomes. The Casimir effect stands out as a brilliant demonstration of this, offering us a rare chance to measure the quantum vacuum's physical push and pull. Picture this scenario. You take a pair of ultra-thin, highly conductive metal sheets and position them incredibly close to one another inside a vacuum, leaving a gap of just a few nanometers. Traditional physics would tell you that absolutely nothing will occur. With no air molecules and no obvious forces at play, it should just be a dead, empty gap. Quantum mechanics, however, tells a completely different story. Since the gap between the metal sheets is so incredibly tight, Only virtual particles with specific, matching wavelengths can squeeze inside. Out in the open space surrounding the plates, no such spatial limits apply. Because of this, a greater number of virtual particles bombard the outside of the plates compared to the inside. This difference in quantum pressure generates a physical push that forces the two metal sheets together. That push is the Casimir effect. Although the force is minuscule, highly controlled laboratory tests have successfully recorded the plates moving toward each other, perfectly matching theoretical calculations. It is almost as though the empty space itself is physically crushing them, demonstrating that nothing actually possesses a physical weight. This underlying energy of the void extends far beyond clever laboratory tricks. It shapes the cosmos on a grand scale. Cosmologists study vacuum energy density, which suggests that the inherent power of empty space could be the engine driving the universe's accelerating expansion. We commonly refer to this enigmatic driver as dark energy. Even though it remains deeply mysterious, the idea of a highly active quantum void likely holds the key to understanding it. Yet, we run into a massive mathematical roadblock. When quantum field theory attempts to calculate the total energy contained within the vacuum, the resulting number is astronomically huge. If we use our current understanding of particle physics to tally up the universe's vacuum energy, the theoretical total overshoots our actual astronomical observations by a staggering 120 orders of magnitude. Scientists frequently joke that this is the single worst prediction in the history of physics, and a true solution remains elusive. Still, this massive discrepancy only underscores how incredibly intricate and baffling empty space truly is. Zooming back down to the subatomic level, these temporary particles act as crucial supporting actors in numerous other bizarre quantum events. Take quantum electrodynamics, for example. The way charged objects interact relies heavily on a continuous trade of virtual photons. This endless swapping is exactly what creates the electromagnetic force we feel in our daily lives. Furthermore, the actual mass of a proton is heavily influenced by a chaotic cloud of virtual gluons and quarks constantly popping in and out of existence within it. The solid, stable matter we take for granted is actually just the end product of dancing with this unseen, jittery vacuum. Even though these ghostly particles flash in and out of reality far too quickly for direct measurement, their fingerprints are everywhere. They cause tiny shifts in the energy states of atomic electrons and add to the magnetic properties of fundamental particles. They are deeply stitched into the very fabric of how nature operates. While this all sounds like pure fantasy, rigorous testing backs it up. When physicists adjust their mathematical models to account for these vacuum jitters, such as when explaining the famous Lamb shift in hydrogen atoms, the theoretical numbers align with physical reality with astonishing precision. The equations might look bizarre, and the ideas might feel crazy, but the experimental proof is rock solid. You could easily argue that this quantum void serves as the ultimate foundational field of reality. All other fields, whether nuclear, gravitational, or electromagnetic, are nested inside of it. They vibrate and wave across its backdrop, much like musical instruments playing a melody over a continuous, never-ending bass line. Many researchers even believe that this empty space hides the secrets to the universe's deepest mysteries. Could it be the ultimate origin point for all cosmic structure? Could it hold the missing puzzle pieces for understanding space-time or quantum gravity? While these remain unanswered questions, one fact is absolutely certain. Empty space is not just a lazy, passive canvas. It is highly dynamic, intricately organized, and bursting with latent potential. Even out in the most freezing, desolate stretches of the cosmos, far away from any matter or starlight, this quantum foundation persists. it continues to vibrate and buzz, quietly broadcasting the fundamental laws of reality to anyone paying attention. It is a deeply humbling realization that a true void is an illusion. Even when everything appears perfectly still, the cosmos is absolutely swarming with secret motion. During the tiny pauses between seconds, within the empty gaps separating atoms, and across the vast dark stretches between galaxies, the action never stops. Our universe is not a silent, dead theater. It is a living stage that constantly rumbles right beneath us. We might not be able to hear this cosmic rumbling with our bare ears, but science has built the tools to tune into its frequency. The empty space vibrates, temporary particles flash in the dark, and the entire universe grooves to a beat that we are only just starting to comprehend. As those fleeting particles dance in the void and the cosmos pulses to its newly discovered rhythm, we must confront a bizarre shift in the narrative. The microscopic realm refuses to follow a traditional script with a neat setup, climax, and resolution. Instead of moving in predictable, linear trajectories, subatomic entities float within hazy clouds of likelihood. They exist in multiple states simultaneously, link across vast distances, and occasionally phase straight through impenetrable barriers. Yet, the most baffling plot twist emerges when we introduce a distinctly human action into the mix: the act of looking. Simply pointing a measuring instrument at a quantum system appears to provoke a radical transformation, fundamentally altering its core nature. Scientists refer to this dramatic shift as the collapse of the wave function. Prior to any observation, an entity such as a photon or an electron is defined entirely by its wave function. This purely mathematical construct encapsulates every conceivable scenario regarding the particle's location and behavior. Rather than occupying a single coordinate, the electron exists as a mixture of countless potential positions. Its rotational spin isn't strictly pointing up or down. It encompasses both orientations simultaneously. It hasn't selected a single route. It is traveling every conceivable path at the exact same time. You can picture this wave function as a glowing, uncertain mist of probabilities. However, the moment you activate a sensor to check on it, everything changes. You essentially demand to know its exact location. And in that precise fraction of a second, the wave function shatters. The misty cloud instantly condenses, forcing all those swirling, overlapping potentials to crystallize into one concrete reality. Suddenly, the electron is pinned down to a single exact coordinate. Its spin commits to either an upward or downward direction, abandoning the dual state. Furthermore, this transition lacks any gradual fade-out period. It doesn't slowly ease into a final state. Rather, it switches abruptly and absolutely. 1 millisecond, the entity is exploring all options in superposition, and the next, it is firmly locked into a single, undeniable condition. It feels as though the cosmos, after pausing to consider its options, makes a definitive choice the very second we check its work. This phenomenon is bizarre enough, but the mystery deepens because the exact trigger for this collapse remains entirely unknown. Could it be the physical bump of a sensor? Is it the mere flow of data? Does human awareness play a role? Could a mechanical lens or even a random insect flying through the laboratory cause it? Honestly, despite being a foundational pillar of quantum mechanics, the mechanics of this collapse remain profoundly elusive. It might very well stand as the most perplexing enigma in contemporary science. To tackle this puzzle, physicists have developed various frameworks, each offering a unique perspective. The most classic framework is the Copenhagen interpretation, heavily promoted by Werner Heisenberg and Niels Bohr. According to this school of thought, the wave function lacks any tangible physical substance. It merely serves as a mathematical instrument to forecast odds. The collapse occurs strictly when an observation extracts data. Prior to that moment, Inquiring about the particle's true state is considered a pointless exercise. The electron isn't hiding in a specific spot waiting to be discovered. It genuinely lacks a specific location until the measurement occurs. While highly practical and excellent for making the equations function, this perspective frustrates many researchers because it fails to define what constitutes a measurement or explain the underlying reason for the collapse. Conversely, the many worlds interpretation completely discards the concept of collapse. Under this framework, the wave function remains intact forever. Every single potential outcome actually occurs just across different branches of reality. If you check an electron spin, the cosmos fractures. One branch features an upward spin, while a parallel branch features a downward spin. You only perceive one result, but the alternative continues to play out in a parallel dimension. This eliminates the collapse mystery entirely, replacing it with endlessly branching timelines. It aligns beautifully with the mathematics, but it demands an endless proliferation of universes, scattering new realities like cosmic dust with every single interaction. On the other hand, objective collapse theories attempt to ground the phenomenon in physical reality. They propose that the wave function is a tangible entity that randomly and spontaneously collapses on its own without needing an observer. Measurements simply elevate the odds of this spontaneous event. By introducing novel physical laws, these models suggest collapse is an inherent natural process rather than an observational artifact. Then we have cubism, a highly unconventional and modern perspective. It argues that the wave function doesn't map the particle at all, but rather maps the observer's personal beliefs regarding the particle. It functions as a subjective calculator for expectations. Consequently, collapse isn't a physical event in the world, but a psychological update in the observer's mind. Much like adjusting your expectations after learning a new piece of trivia, the external world remains unchanged. Only your internal model shifts. While some researchers love this fresh take, others hate it, arguing that physics should describe the cosmos, not human psychology. Finally, decoherence offers a partial explanation by detailing how quantum effects fade in macroscopic objects. When a microscopic system bumps into its surroundings, perhaps interacting with a few random light particles, it becomes entangled with the broader environment. This environmental entanglement washes out the delicate interference patterns required for superposition. The system appears to have collapsed to our eyes, explaining why macroscopic objects like cats don't exist in dual states of life and death, even if it doesn't fully explain how a single final outcome is selected. So here we remain. Over 100 years since quantum mechanics was born, this collapse mechanism continues to haunt the equations like a phantom. The mathematical formulas are spectacularly successful, allowing us to forecast experimental results with astonishing accuracy. Yet the fundamental questions persist. What exactly is collapsing? When does it happen? What is the underlying cause? Is the collapse even a genuine physical event, or are we simply hitting the boundaries of human comprehension? Theories abound. Some experts argue we require an entirely new framework for measurement or a deeper foundational theory that supersedes current quantum rules. Others are perfectly fine with the mystery, arguing that as long as the predictions are accurate, the rest is merely philosophical debate. However, philosophy is crucial in this context because this issue extends far beyond subatomic particles. It strikes at the very fabric of existence. Is the cosmos inherently based on chance? Does it rely on an observer to exist? Is it continuously fracturing into new timelines? Is it molded by data, awareness, or some undiscovered force? What are the ultimate limits of human knowledge? You might view the collapse as the exact boundary where the quantum realm transitions into the classical world. similar to a phase transition, like liquid water turning into solid ice. However, unlike freezing water, the parameters for this quantum transition are completely hidden. We lack the equivalent of temperature or pressure metrics. We simply observe that the misty potential eventually hardens into a concrete presence. It is incredibly easy to get tangled in poetic comparisons. Is the wave function a curtain, a fantasy, or a buffet of potential futures? It could be all of these or none of them. Perhaps the only thing truly collapsing is our stubborn human assumption that the universe must always be rigid and definitive. The cosmos might be perfectly comfortable existing in a state of flux, while we are the ones demanding a final answer. Instead of asking what happens during measurement, perhaps we should ask what we assume happens, and whether we are ready for an answer that defies our hopes but reveals a deeper truth. If the quantum realm had an official capital city, it would undoubtedly be Copenhagen. This isn't due to the picturesque Danish landscapes filled with bikes and wind turbines, but because this city served as the birthplace for the most bizarre concepts in modern science, where they were fiercely debated and eventually embraced. The central figure in this historical drama is Niels Bohr, a physicist from Denmark known for his mild personality and his penchant for delivering incredibly long, intricate sentences. Bohr was instrumental in formulating the Copenhagen interpretation, which remains one of the most dominant paradigms in the field. The core premise is surprisingly straightforward, which is a major part of its enduring appeal. According to this paradigm, microscopic entities possess zero definitive traits prior to being observed. An electron lacks a set coordinate. A photon refuses to lock in a specific polarization. The particle simply refuses to commit to a specific condition until an observation forces its hand. Before the measurement occurs, the universe exists as a blurry haze of odds, functioning purely as a wave of probability. The act of measuring doesn't simply uncover a pre-existing fact, it actively generates the result. To put it bluntly, the physical world doesn't fully materialize until we interrogate it. Such a massive claim naturally excites philosophers and sends physicists scrambling for caffeine. Yet, Bohr and his peers weren't attempting to inject unnecessary magic into the cosmos. They were desperately trying to reconcile their equations with actual laboratory data. Whenever they modeled particles as tiny, solid spheres, their calculation completely failed. However, the moment they treated them as waves of probability that only solidified upon observation, the mathematics aligned perfectly. Within this framework, the wave function lacks physical substance. It doesn't map the actual momentum or location of a particle. Rather, it serves as a comprehensive inventory of everything we could potentially learn about the setup. It is a ledger of possibilities, not a geographical map of reality. This brings us to a primary pillar of the Copenhagen paradigm. Inquiring about the state of a particle before observation is a logical fallacy. Asking about an electron's prior location is nonsensical, because the concept of location only gains meaning after the measurement takes place. You don't pull back a curtain to reveal a hidden reality. The reality actually materializes the second you look. The particle wasn't concealing its true form. It simply hadn't developed one yet. Naturally, this explanation left many brilliant minds deeply frustrated. Albert Einstein was notoriously disturbed by this concept, fiercely advocating for a cosmos that functioned independently of human observation. He championed a deterministic, objective reality that existed even when no one was watching. From Einstein's perspective, the Copenhagen paradigm was equivalent to claiming the moon vanishes when you close your eyes. Bohr pushed back, but he didn't attempt to provide a sweeping philosophical resolution. Instead, he adopted a highly pragmatic, somewhat ambiguous stance. He argued that quantum mechanics dictates what we are permitted to articulate about the natural world, rather than defining the fundamental essence of nature itself. Science, in his view, exists to meticulously document experimental outcomes, not to uncover the hidden gears of the universe. If this feels like a cop-out, you are in good company. Critics frequently attack the Copenhagen paradigm for acting as a set of instructions rather than a true explanation. It teaches you how to manipulate the formulas and forecast the results, but it completely ignores the underlying mechanisms driving the show. This frustration birthed the famous mantra to just shut up and calculate. Although Bohr never actually spoke these exact words, the phrase perfectly encapsulates the attitude of generations of researchers. The underlying message is to ignore the philosophical headaches and simply utilize the mathematics. The formulas are undeniably effective, yielding flawless predictions, which many argue is all that truly matters. Indeed, the Copenhagen method is spectacularly successful. It remains the standard curriculum in universities and laboratories worldwide, forming the foundational logic behind lasers, quantum computers, and modern semiconductors. It has passed every single experimental challenge thrown its way. For a vast number of researchers, this flawless practical record easily eclipses any lingering philosophical doubts. Nevertheless, those doubts refuse to completely disappear. If the physical world only solidifies upon measurement, what happened during the billions of years before conscious beings evolved? Did the early cosmos exist in a frozen state of pure potential, waiting for an observer to trigger reality? The consensus among physicists is a resounding no. The Copenhagen framework doesn't actually demand a conscious mind. It merely requires an interaction with the broader environment or a mechanical sensor. In this context, observation simply means extracting data from the system, forcing it to commit to a specific state. Yet, this clarification only spawns additional queries. What exactly qualifies as a measurement? When precisely does the transition occur? Why does the cosmos operate under such a bizarre restriction? The Copenhagen advocates typically respond with a polite shrug. Their framework specifies the timing of the collapse, but completely ignores the underlying cause. If you demand a deeper mechanical explanation, you must explore alternative models. Frameworks like objective collapse, pilot wave theory, and many worlds all attempt to provide that missing depth, striving to maintain classical intuitions about cause and effect and independent reality. However, every single alternative introduces its own massive complications. The Copenhagen paradigm, by comparison, remains incredibly streamlined. It refuses to invent hidden variables or spawn infinite parallel dimensions. It simply provides a strict set of operational guidelines. Compute the wave function, apply the rules of measurement, and record the prediction. It is straightforward, highly efficient, and remarkably effective. This stark simplicity might be its greatest strength. Amidst a discipline overflowing with mind-bending anomalies, the Copenhagen approach provides a soothing sense of order. It makes no attempt to solve the ultimate mysteries of existence. It is perfectly satisfied with mapping the observable, measurable world without pretending to understand the hidden engine driving it all. For many, that is perfectly sufficient. Bohr frequently communicated through complex, almost lyrical phrasing, famously noting that anyone who isn't profoundly shocked by quantum mechanics has completely failed to grasp it. He recognized that his paradigm wasn't designed to tame the universe. It was designed to help us accept the untamable. The quantum realm is inherently bizarre. Instead of forcing it into a neat classical box, the Copenhagen interpretation encourages us to embrace the absurdity and operate within it, without demanding that the cosmos justify its existence. It isn't the ultimate truth. It is simply a quiet set of rules, reminding us that in the subatomic world, elegance and unease are permanent companions, and sometimes the smartest move is to just shut up and calculate. While shutting up and calculating might be practical, our curiosity inevitably pushes us to ask what actually happens behind the math. To explore this, picture a coin resting in your hand. You toss it, watch it catch the light as it twirls, and hear it hit the table with a gentle tap. It shows heads. Yet, under a specific framework of quantum mechanics, a different event simultaneously occurred. In another realm, not this one, but equally authentic, that exact same coin showed tails. In yet another reality, it balanced perfectly on its rim, tumbled off the desk, and disappeared beneath a sofa. Rather than mere statistical likelihoods, every result of that toss materialized as a distinct physical branch of existence. You simply happen to inhabit the specific timeline where heads faced up. This beautifully bizarre concept forms the core of the many worlds interpretation. Originally conceived as a theoretical exercise, it offered a fresh perspective on the notorious wave function collapse dilemma. Recall the wave function, the mathematical fog of probability describing a quantum system. The conventional Copenhagen interpretation dictates that observing the system forces this fog to collapse, solidifying a single reality. However, what if that collapse is an illusion? In 1957, physicist Hugh Everett III introduced a groundbreaking alternative. He suggested the wave function progresses continuously and predictably without ever collapsing. When you observe a quantum system, you aren't forcing it to pick a single path. Rather, you divide. The entire cosmos fractures. Every conceivable result manifests, but each unfolds within its own isolated slice of reality. While this sounds like sci-fi, Everett was strictly dealing with equations. Mathematically, his framework perfectly mirrors standard quantum mechanics. It merely deletes the arbitrary rule demanding a collapse upon observation. From his perspective, the wave function simply divides. To visualize this, picture an electron that can spin either up or down. Traditional theory claims the electron exists in a blended superposition until observed. Everett argued no selection is ever made. Instead, measuring entangles the observer with the system, splitting both into two synchronized realities. In one timeline, you record an upward spin, in the other, a downward spin. Both results are completely genuine. Two distinct versions of you now exist in separate cosmic branches. There is zero randomness, just an ever-expanding tree of physical reality. Although this evokes images of infinite doppelgangers, the many worlds interpretation is firmly grounded. It introduces zero new physical laws. Its charm lies in strictly adhering to established mathematics, rejecting the mystical assumption that observation triggers a magical change. Fans champion its mathematical purity. The concept is strange, but the equations remain neat. Naturally, this makes many uneasy. If reality perpetually fractures, where are these new universes located? The theory remains silent because it addresses the evolution of quantum states rather than the physical architecture of space. Once a division happens, the newly formed branches undergo decoherence. They cease to interact, rendering them practically invisible. This isolation makes verification difficult, leading to the main critique. If we cannot see these branches, is the theory falsifiable? Advocates counter the goal isn't novel predictions, but eliminating superfluous assumptions. Since the Schrödinger equation dictates smooth evolution and never mentions collapse, why invent it? Occam's razor can be wielded by both sides. Copenhagen maintains a single universe by inventing a complex collapse rule. Conversely, Many Worlds preserves mathematical simplicity by embracing an infinitely vast cosmos. But just how massive is this cosmos? Pause to grasp the sheer magnitude. The universe fractures whenever a quantum event presents multiple outcomes. This includes every molecular bump, radioactive breakdown, and emitted photon. Reality is dividing at an exponential, mind-boggling rate every fraction of a second. Yet, much like we remain oblivious to the Earth's rapid rotation, we are entirely blind to this cosmic fracturing. The process is so seamless we only perceive a single result. Crucially, these alternate realities do not function like pop culture parallel dimensions. You cannot jump between them, nor will you ever bump into an alternate self. Every branch is strictly sealed off, forbidding cross-reality contact. You cannot peek into a neighboring timeline to see if your alternate self chose soup over salad. Once the split occurs, it is absolute. This isolation resolves many philosophical puzzles tied to wave function collapse. Physicists no longer debate what qualifies as an observation. The universe just flows smoothly. Observation is merely entanglement, where you and the quantum system intertwine. Yet, this elegant framework introduces its own puzzle. If every result occurs, why do we experience the illusion of a single outcome? Why does it feel like the coin definitively landed on heads? If everything happens, how do we define probability? Many worlds completely reimagines probability. Rather than the likelihood of an event, probability measures how much of you ends up in a specific branch. Instead of asking about the odds, you evaluate what percentage of your future selves witness a result. While not intuitive, it perfectly matches the counterintuitive nature of quantum physics. Despite its bizarre implications, this framework sparked profound scientific exploration. Some researchers suspect it might hold the key to merging quantum mechanics with gravity. Others view it as the bedrock for quantum computing, where entangled states perform massive calculations across countless possibilities. Personally, this perspective offers profound peace, or perhaps lingering unease. Under this model, nothing is ever truly erased. The paths you chose not to walk still actively unfold in parallel timelines as tangible events. Rather than making you feel insignificant, this suggests reality is far more abundant than we imagined. The cosmos isn't just a single narrative. It is a glittering archive where every outcome is permanently etched into existence. So avoid picturing a chaotic jumble of cartoonish dimensions. Instead, envision a serene, ever-growing tree. Every twig represents a distinct journey, every leaf a complete world, and every outcome a beautiful verse composed in the language of physics. And in their own unique way, every single one of them is entirely true. Building on those profound truths, let us peel back the ultimate layer of reality. Picture the cosmos, the deep seas, your chair, your fingers, and the soft sunlight on your bed. Suppose none of this physical substance actually consists of solid objects. Instead of tangible blocks, the foundational essence of existence might actually be oscillations and unseen waves, propagating across invisible domains. Step into the subtle realm of quantum field theory, a framework where shimmering background domains, rather than discrete specks, construct our reality. To ease into this, consider how traditional science defines these domains. Essentially, they allocate a specific numerical property to each coordinate in the void. Think about electromagnetism as a prime illustration. This unseen influence dictates the trajectory of electrically charged objects. Drop a positively charged item into this region, and it immediately experiences a physical shove. These continuous, seamless expanses permeate the cosmos much like an unseen, frictionless gelatin. Then subatomic principles introduce inherent unpredictability. These expansive regions refuse to remain perfectly still. They constantly vibrate and hum, regardless of whether physical matter is present. Whether discussing magnetism, electricity, or gravity, every domain exhibits this subatomic jitter. They tremble continuously, even when appearing completely barren. Consequently, the void of space is never genuinely tranquil. It remains perpetually agitated and brimming with hidden activity. This brings us to the grand revelation. Within this paradigm, absolutely everything consists of these foundational domains. All the famous subatomic specks, like quarks, neutrinos, photons, and electrons, are merely minor disturbances within their respective expanses. Rather than picturing a minuscule solid sphere zooming through the void, imagine a concentrated wave. These physical entities are simply concentrated bumps propagating through the foundational fabric permeating all of existence. Consider the electron. A specific subatomic domain dedicated to electrons stretches across the entire cosmos. Observing one means you are not witnessing an isolated item. Instead, you are detecting a highly specific, quantized surge of energy within that universal expanse. A concentrated burst of activity occurs, and we label that disturbance an electron. The exact same logic applies to light. An electromagnetic expanse saturates the cosmos. A speeding photon is not a microscopic projectile. It is a tiny tremor within that domain. Adjust the frequency of that tremor, and you perceive visible illumination. Alter it again, and you generate X-rays. Ultimately, these are merely different rhythmic expressions of the exact same expanse. A dedicated domain exists for every recognized subatomic entity, including gluons, quarks, and the Higgs boson. Even the hypothetical graviton would simply represent a tremor within the domain of gravity. So what happened to the traditional concept of a solid speck? Essentially, these discrete objects act as a practical illusion, offering a convenient shorthand to explain domain behavior. Whenever a disturbance concentrates into a distinct packet of energy, we apply the label of a discrete object. However, that terminology merely describes an action. The underlying expanse remains the true foundational reality. We observe the wave, but the domain is the actual substance. Adopting this viewpoint drastically alters our cosmic perspective. Rather than viewing the cosmos as a collection of microscopic bricks, we can envision a grand musical composition. Reality materializes from the beautiful harmony of an endless orchestra of vibrations. Furthermore, this framework elegantly resolves bizarre subatomic mysteries. How do physical entities spontaneously appear and vanish during extreme energy collisions? The answer is straightforward. They are merely surges of domain activity. Concentrate immense energy into a tiny zone, and you vibrate the underlying expanse violently enough to generate a brand new wave. This exact mechanism allows facilities like CERN to manifest completely novel entities from seemingly empty space. Then we must consider antimatter, such as the positron, the shadowy counterpart to the electron. Within this paradigm, antimatter simply represents an alternative vibrational pattern within the exact same domain, exhibiting reversed characteristics. There is no supernatural mystery here, only beautiful mathematical symmetry. An especially elegant revelation is that fundamental forces are also transmitted through these domains. Electromagnetism occurs when charged entities swap photons, which are just waves in the electromagnetic expanse. The strong nuclear force relies on gluons oscillating within their specific domain to glue quarks together. Meanwhile, gravity, assuming we eventually quantify it, would rely on minuscule gravitational waves known as gravitons. Consequently, a true void does not actually exist. This framework dictates that these foundational expanses never achieve absolute stillness, constantly trembling with vacuum fluctuations. Such endless jittering produces tangible physical consequences, perfectly illustrated by the Casimir effect. Here, a pair of metallic sheets positioned extremely close in a void experience an attractive pull, driven by shifting energy levels between them. This concept offers a deeply peaceful cosmic vision. The void is not a passive stage, it actively participates in reality. Every coordinate brims with latent possibilities, meaning all physical interactions and light beams are simply the domain expressing its inherent nature. Naturally, the mathematics behind this framework are incredibly complex. You cannot casually scribble the equations on a small napkin unless that napkin spans an entire chalkboard and you are drawing intricate Feynman diagrams. Yet the core philosophical message remains beautifully simple. The deepest layer of nature consists of energetic patterns distributed across space and time rather than solid objects. Even the stubborn property of physical mass often emerges purely from interactions within these domains. The Higgs domain, confirmed by experiments in 2012, grants mass to numerous subatomic entities. These entities navigate this specific expanse much like people swimming through thick syrup. Experiencing greater drag directly translates to possessing heavier mass. This means we exist immersed in a vast ocean of these domains. As you absorb these words, you represent an intricate pattern woven through the photonic, quark, and electronic expanses. Your consciousness consists of complex vibrational patterns. The atoms constructing your physique act as interconnected nodes within a massive cosmic web, vibrating in perfect harmony. Your physical form does not abruptly stop at your skin. The foundational domains constructing your identity extend outward into the cosmos. You possess no rigid borders, only fluctuating waves dissolving into the vast ocean of subatomic existence. This framework does not merely explain the cosmos, it fundamentally embodies it, serving as the most accurate cartography humanity has drafted. It maps a reality constructed not from colliding objects, but from intricately woven domains performing an infinitely swift, subtle dance. Ultimately, if all physical existence is just a wave, one final mystery remains. What exactly is the medium these waves travel through? That profound puzzle is a question for another dream. Leaving that profound puzzle for another dream, let us explore the pieces we actually understand. If the universe came with a master recipe book, the standard model of particle physics would serve as the ultimate ingredient list, excluding a couple of enigmatic seasonings like dark energy and dark matter. Its inventory is remarkably concise. It boasts a beautiful organizational structure, even if the naming choices are a bit wild. Despite its eccentricities, this framework stands as one of the most triumphant scientific theories ever devised. It explains the fundamental composition of reality, the ways these components engage with one another, and the underlying reasons for the universe's behavior. Let us meet the main characters. Fundamentally, this framework consists of elementary particles. As far as our current knowledge extends, these tiny entities cannot be split into anything smaller. Picture them as the ultimate foundational bricks of matter and energy, all interconnected through the fabric of quantum fields. We can sort them into three primary categories: bosons, leptons, and quarks. Quarks form the solid center of atoms, specifically building protons and neutrons. We recognize 6 distinct varieties, often called flavors: up, down, strange, charm, bottom, and top. And yes, scientists actually chose those labels. Researchers can execute the most complex calculations known to humanity, but when it comes to naming their discoveries, absolute madness takes over. The most abundant and lightweight varieties are the up and down quarks. A proton contains 1 down quark and 2 up quarks. A neutron holds 1 up quark alongside 2 down quarks. Consequently, your body and everything else in your physical environment primarily consists of electrons and these up and down quarks. The remaining 4 flavors are much heavier and far less common, typically encountered only in extreme high-energy situations like cosmic ray impacts or particle colliders. Think of them as the particle equivalent of celebrity cameos. Brilliant, incredibly brief, yet vital to the overall production. Moving on, we find the lepton family. This category features the famous electron, a particle you already know well from its role in generating electricity, orbiting atomic nuclei, and enabling life. However, electrons have heavier relatives. The muon acts like a beefed-up electron, while the tau is even more massive. Similar to the exotic quarks, these heavyweight leptons are highly unstable in normal conditions, only appearing during intense energy reactions and leaving specific signatures behind. Furthermore, every charged lepton is paired with a neutral companion known as a neutrino. We have 3 distinct neutrino flavors. They are astonishingly fast, remarkably light, and completely antisocial. Neutrinos almost never engage with regular matter. Right now, billions of them stream directly through your body every single second, completely undetected. They act as the ultimate introverts of the cosmos. Adding it all up, we have 12 matter particles, 6 leptons and 6 quarks, neatly organized into 3 generations, performing their routines across the stage of quantum fields. Yet, a universe requires more than just raw material. We also need the forces dictating how all these particles behave around each other. This brings us to the bosons, the messengers of force. Every basic force utilizes a specific carrier particle, functioning like a subatomic handshake. Take the electromagnetic force. Its messenger is the photon, which we experience as light. Having 0 mass, photons travel at light speed and keep electrons attached to atoms. Without them, we would have no chemistry and no breakfast. Next is the weak nuclear force driving radioactive decay. This force relies on 3 heavy bosons, the Z, the W-, and the W+. Because of their massive weight, they only operate across extremely tiny distances, facilitating the transformation of protons into neutrons and vice versa to drive stellar fusion. Then we have the strong nuclear force, the ultimate adhesive binding quarks together to form neutrons and protons and holding atomic nuclei intact. The gluon serves as its carrier. Massless but highly energetic, gluons come in 8 types. Picture them as hyperactive toddlers in a ball pit, endlessly swapping energy and refusing to stay still, serving as the sole reason your physical form does not disintegrate. Finally, we must mention the Higgs boson, verified at CERN in 2012 and leading to a Nobel Prize the very next year. This particle represents the Higgs field, an invisible energy field stretching across space that grants mass to various other particles. Without it, most particles would zip around massless, completely incapable of forming atoms. To summarize, we have 12 matter particles alongside 5 force-carrying bosons, the Higgs, gluon, CW, and photon. This ensemble functions spectacularly well, successfully forecasting the results of innumerable tests with mind-boggling accuracy. Whether looking at radioactive decay or particle colliders, this framework consistently proves itself correct. Naturally, there are missing pieces. First, gravity is entirely absent. The standard model operates purely as a quantum framework, whereas gravity is explained by Einstein's classical general relativity. Combining these remains a massive unresolved challenge. Furthermore, dark matter is invisible and ignores light entirely. Our current inventory cannot explain the gravitational effects we observe across galaxies. We also cannot ignore dark energy, the mysterious phenomenon driving the expansion of the cosmos to accelerate. Ultimately, this celebrated framework only accounts for roughly 5% of the universe. Yet, what an incredible 5% it is. Every single atom, every interaction, every flash of light, and every breath you draw is governed by this beautiful, shimmering web of particles. People often describe the model as complete, yet leaving you wanting more, like finishing a puzzle only to realize the box image was merely a tiny fragment of a much grander landscape. Even so, the completed section is breathtaking, featuring gorgeous mathematical symmetries suggesting a deeper harmony. Many physicists hope these particles might eventually combine into a single grand unified theory, or perhaps a theory of everything. While such aspirations remain out of reach for today's experimental technology, they are driven by the conviction that the natural world can be understood and that hidden order exists beneath apparent randomness. So the next time someone asks what the universe is constructed from, smile and reply, mostly quarks, a handful of bosons, and a few leptons. Then add, and remember the Higgs field, because without it, absolutely nothing would have any weight. It might not be the entire story, but it is a magnificent opening chapter. Building on that magnificent opening chapter, we now arrive at a concept where staggering mathematical elegance meets mind-boggling complexity, often considered the absolute pinnacle of physical science. Quantum electrodynamics, commonly abbreviated as QED, serves as the ultimate rulebook for the interactions between light and physical matter. The sheer exactness of this framework is so profound that it leaves even the most meticulous mathematicians completely astounded. Fundamentally, this theory maps out the intricate subatomic ballet shared by photons and electrons. Whenever you see a flash of light, witness a spark, or observe the magnetic attraction and repulsion of charged particles, you are watching a show directed entirely by QED principles. Even though the calculations require factoring in limitless potential interactions and utterly baffling odds, the ultimate conclusions align with physical experiments in a way that defies belief. To put this phenomenal accuracy into perspective, the predictions are verified to a margin of error smaller than 1 part in a single billion. Imagine calculating the exact distance across the entire North American continent and missing the true mark by no more than the width of a single strand of human hair. To understand how such flawless results are achieved, we must first look at the historical headache this framework resolved. During the first few decades of the 20th century, scientists understood that the electromagnetic field and electrons were connected. They knew that light is released when an electron speeds up, and that absorbing light causes an electron to shift its energy state. However, attempting to map out the precise mechanics of these exchanges on a subatomic scale proved to be an absolute mathematical disaster. The formulas simply shattered. Meaningless infinities kept popping up in the calculations. If you attempted to calculate the energy of a single photon being released by an electron, the equations would output an infinite amount of energy, a rather useless result, unless your goal was to instantly incinerate the whole cosmos. The solution arrived courtesy of Richard Feynman, a brilliant researcher famous for his playful personality and his hobby of playing the bongos. Working in tandem with Sin-Itaro Tokunaga and Julian Schwinger, Feynman figured out how to tame these unruly equations. Yet, Feynman pushed the boundaries even further by translating the abstract math into visual concepts. He created Feynman diagrams, which are simple illustrations that transformed agonizingly difficult quantum math into something resembling basic doodles. Within these sketches, straight and wavy lines represent different particles, while the progression of time moves horizontally across the page. For instance, a line representing an electron could travel inward, release a photon, and keep moving forward. The newly created photon might then travel outward to strike a different electron, or it could curve back to influence the original particle. Every single trajectory in these drawings corresponds to a specific mathematical formula, and the rules of QED dictate that you must sum them all together. You do not merely calculate the most probable route, you must include every conceivable variation of the event. This means factoring in some truly bizarre scenarios. For example, an electron might release a photon that temporarily splits into a positron and an electron, which then crash into each other to form a new photon that gets reabsorbed. Scientists refer to these fleeting entities as virtual particles. Although they only live within the theoretical gaps between observable physical events, their impact on the final result is entirely tangible. At this stage, the subject transcends standard physics and feels more like a beautiful poem composed entirely of calculus. The framework calculates not only the events that actually occur, but also every single event that theoretically could occur. Every single twist, turn, and loop contributes to the ultimate calculation. Miraculously, when you blend all these countless probabilities together, the resulting forecast is so incredibly sharp that it could predict the exact behavior of a single electron located at the opposite end of the Milky Way, accurate to the smallest fraction of a decimal. A major victory for this framework is its flawless description of the electron's anomalous magnetic moment. Because an electron generates a minuscule magnetic field, it acts somewhat like a tiny bar magnet. While traditional physics can estimate the power of this magnet, subatomic phenomena alter that strength by a microscopic amount. QED successfully computes this exact microscopic shift, aligning with physical measurements out to more than 10 decimal points. Calling this achievement merely good is a massive understatement. It is absolutely breathtaking. Furthermore, the model provides a beautiful explanation for various other occurrences. It perfectly describes Compton scattering, which is the bouncing of a photon off an electron. It clarifies Bremsstrahlung, the release of radiation that happens when a particle decelerates. It also details pair production, the astonishing process where pure light converts into both antimatter and regular matter. Even though these terms sound like magical incantations from a science fiction novel, they are all straightforward consequences of QED principles. It is important to note that this framework operates within a broader scientific context. While it specifically functions as the quantum field theory for electromagnetic interactions, it also served as the foundational blueprint for subsequent theories. For instance, the strong nuclear force is explained by a similar model known as quantum chromodynamics. Meanwhile, the weak nuclear force is governed by electroweak theory, a framework that successfully merges the weak interaction with electromagnetism. Nevertheless, QED was the pioneer that established the gold standard for all these subsequent discoveries. There is also a rather delightful aspect to all of this. Even though the underlying mathematics can seem utterly overwhelming, the core concepts become remarkably intuitive once you grasp the basics. Feynman frequently joked that you could summarize the entire rulebook of QED on the back of a cocktail napkin. With his characteristic flair, he simplified the concept to its absolute essence. Particles travel along every conceivable route, with each route assigned a specific probability amplitude. To discover the true likelihood of an event, you simply add these amplitudes together and square the result. Everything else is merely administrative math. This principle, that the natural world tests out every single route, forms the very foundation of quantum mechanics. When an electron moves between two locations, it does not simply travel in a straight line. Instead, it simultaneously navigates every conceivable trajectory, weaving through all barriers, circling every object, and passing beneath every structure in existence. The cosmos is constantly processing all these infinite options, and QED provides the lens through which we can observe this grand calculation. This framework perfectly illustrates just how bizarre the subatomic realm can get, while still remaining mathematically sound. You might assume that such an eccentric model must eventually hit a wall, and you would be entirely correct. The theory completely ignores gravitational forces and offers zero insights into the mysteries of dark matter. However, within its specific area of expertise, it remains utterly unmatched. It stands without question as the most rigorously verified concept in the entire history of scientific inquiry. Even Feynman, a man known for his disdain for blind hero worship, confessed that the achievements of QED were truly phenomenal. Yet, he also cautioned scientists against becoming overly complacent. He frequently reminded his peers that the natural world always keeps a few more secrets hidden away. Consequently, while this framework represents the pinnacle of our current understanding, it might not represent the absolute limit of what humanity can eventually comprehend. Regardless of future discoveries, it remains an undeniable masterpiece for the time being. What started as a frustrating mess of philosophical confusion and broken equations has blossomed into a beautifully clear explanation of the universe's subatomic pulse. It captures the endless, quiet conversation between physical matter and light, articulated with such breathtaking elegance that the numbers themselves seem to applaud. Hidden within that silent conversation is the brilliant shine of faraway suns, the vibrant pixels of your mobile phone, and the soft, warm light of your bedroom lamp. A remarkably understated framework orchestrates all of these phenomena, operating so smoothly that you never even realize it is there. Yet, it governs every single flash of light, every mirrored reflection, and every tiny photon of brightness. Quantum electrodynamics stands as a silent victory, a magnificent routine composed of photons and force fields, executing flawlessly billions of times every single second, always hitting its mark perfectly on cue. While quantum electrodynamics perfectly orchestrates the silent dance of photons and force fields, another realm of quantum mechanics is stepping into the spotlight to completely redefine how we process information. Think of a traditional computer as a highly disciplined librarian, efficiently turning through books one page at a time. A quantum computer, however, acts more like an eccentric poet who absorbs every book simultaneously through overlapping whispers, yet still extracts the perfect answer. Although this feels almost mystical, it is grounded in the strange realities of quantum physics. To grasp why these machines are unique, we must meet the qubit, the quirky relative of the standard bit. Inside your everyday device, all data is reduced to basic bits. Functioning as simple binary switches, they are strictly locked into a state of 0 or 1. They form the foundation for every digital task, from streaming videos to calculating taxes. Traditional machines excel at shuffling these switches at lightning speed. A qubit, however, refuses to be confined to just 0 or 1. Thanks to superposition, it exists as a mixture of both states simultaneously. Picture a coin spinning rapidly in the air. Until it lands and you observe it, it is not strictly heads or tails. It holds the potential for both. In this spinning state, a single qubit carries multiple realities at once. When you link these qubits together, their computational muscle expands exponentially. 2 qubits represent 4 combinations. 3 give you 8. By the time you reach 20 qubits, you are looking at over 1 million simultaneous possibilities. With enough qubits, a quantum machine can theoretically navigate an astronomical array of options in parallel. This massive parallelism is the core secret. Instead of checking every route sequentially like a classical machine, a quantum system investigates countless pathways at once. This does not mean it magically spits out every answer instantly. The real genius is in how the system is guided. Rather than relying on brute force guessing, scientists shape the probability landscape. They manipulate the quantum states so that when the final measurement occurs, the correct solution has the highest chance of appearing. Then we have the second major advantage, entanglement. When qubits become entangled, their states become deeply intertwined, regardless of physical distance. This creates complex correlations that standard bits could never achieve. Imagine a synchronized dance between 2 particles. If one partner twirls, the other instantly mirrors the spin, no matter how far apart they are. This deep connection enables quantum processors to execute calculations that would drain massive time and power from classical supercomputers. For specific challenges like modeling molecules or factoring massive numbers, this approach offers staggering speedups. Let us take a step back, though. You will not be trading in your laptop for a quantum model anytime soon. These are highly specialized instruments, not everyday gadgets. For standard chores like surfing the web or editing videos, your trusty classical computer remains the undisputed champion. Furthermore, building and operating these machines is incredibly difficult. Qubits are notoriously fragile. The slightest vibration, minor temperature shift, or rogue magnetic field can ruin their state. Keeping a qubit coherent, maintaining its superposition and entanglement, demands extraordinary care. Many processors must be chilled to temperatures near absolute zero, making them colder than deep space. Then we face error correction. If a standard bit flips, classical systems easily spot and repair it. Quantum systems do not have it so easy. Because of the no-cloning theorem, you cannot simply duplicate a qubit state without destroying the original information. To bypass this, scientists use large groups of physical qubits to safeguard a single logical qubit. It is like wrapping our whispering poet in thick, soundproof padding, so their recitation is not interrupted. Despite these obstacles, progress is rapid. Labs are running machines with dozens to hundreds of qubits. Some have achieved quantum supremacy, completing calculations that would take traditional supercomputers an impractical amount of time. Others are experimenting with NISQ devices, noisy intermediate-scale quantum machines, which explore what we can do with imperfect but useful quantum systems. Real-world applications are already taking shape. Quantum chemistry is a huge focus. Because classical computers struggle to model molecular behavior at the subatomic level, quantum machines are perfectly suited for the task. This could revolutionize drug discovery, material science, and battery technology. Optimization is another major target. When dealing with complex puzzles involving countless variables, like mapping delivery routes, quantum algorithms could pinpoint solutions much faster. Finally, there is cybersecurity. Algorithms like Shor's algorithm could one day shatter current encryption by rapidly factoring enormous numbers. This has sparked post-quantum cryptography, a field dedicated to creating unbreakable, quantum-proof code. Nevertheless, we are in the early days. Today's processors remain noisy, fragile, and limited. A fully stable large-scale quantum computer is likely years or decades away. Yet, the journey is captivating. The most beautiful aspect is how it takes the most baffling quirks of quantum mechanics, concepts that once seemed like philosophical puzzles, and transforms them into practical tools. Superposition shifts from a curiosity into a resource. Entanglement goes from spooky to highly functional. Even measurement, which collapses possibilities into a single reality, becomes a crucial calculation step. It is almost poetic. The exact bizarre traits that made quantum physics so unsettling are now harnessed to solve previously impossible problems. It is like taming a fierce wind. Instead of fighting it, we are learning to sail with it. Quantum computing forces us to reimagine calculation, blurring the lines between logic and fuzzy probability. It reminds us that beneath our classical reality lies a profoundly weird domain where data is soft and tangled, and answers emerge from beautifully orchestrated patterns of possibility. We may not know exactly where this path leads, but the voyage itself, quiet, intricate, and full of potential, is already rewriting what machines and minds can achieve. While human engineering pushes the boundaries of what machines can achieve in sterile environments, the natural world has quietly mastered these same bizarre principles for eons. We expect the quantum realm to be strange, picturing tiny particles phasing through solid walls, rotating in opposite directions simultaneously, and sharing invisible connections across vast distances. Yet, the last place we expect such delicate phenomena is inside living organisms, which are inherently chaotic, humid, and warm. They function in a turbulent environment packed with bouncing atoms, erratic crashes, and shifting energy levels. Conversely, quantum states are incredibly brittle, easily shattered by a little thermal energy or environmental noise. This exact fragility is why researchers construct quantum processors inside ultra-chilled facilities and suspend particles within extreme vacuums. Despite these harsh biological conditions, living creatures appear to be harnessing quantum mechanics for their own benefit. Consider the European robin, a modest avian creature possessing an extraordinary navigational talent. These birds undertake massive migrations, traveling immense distances with startling accuracy. What exactly directs their flight path, and how can they pinpoint true north? Researchers have long hypothesized that these animals possess an internal magnetic compass, yet the exact mechanical workings stayed a mystery. Then a groundbreaking theory emerged. Perhaps quantum entanglement plays a crucial role. The proposed mechanism suggests a specific retinal protein, likely cryptochrome, houses a duo of entangled electrons. As sunlight strikes this protein, it energizes the electrons, forcing them into a state of quantum linkage. The spin states of these connected particles then react to the planet's magnetic field, altering a specific chemical response that shifts depending on the exact heading of the bird. If this sounds far-fetched, you are in good company. The scientific community initially greeted the proposal with heavy doubt. Since entanglement is so easily broken, how could it possibly endure within a chaotic cellular environment, surrounded by splashing water and moving proteins? Astonishingly, preliminary studies indicate that it actually can. An increasing body of research points toward birds genuinely depending on quantum phenomena to sense magnetic orientations. While the case is not entirely closed, the initial data looks highly encouraging. Should this hold true, it implies nature has discovered a method to maintain quantum states within a messy biological framework. An achievement human technologists are still fighting to replicate. Moving from avian navigation to the botanical kingdom, we find flora excelling at a highly refined quantum strategy. Think about photosynthesis, the mechanism allowing greenery to convert solar radiation into usable chemical fuel. The premise seems straightforward. Photons strike a chlorophyll structure, the energy is absorbed, and it is passed to a central reaction hub for storage. The real puzzle is how this energy travels with such flawless efficiency. You might assume the energy randomly bounces from molecule to molecule until it accidentally finds its destination, but such a trial and error approach would be incredibly sluggish. Instead, observations point to a much more sophisticated process. The absorbed energy seems to test numerous routes at the exact same time, utilizing quantum coherence to identify the absolute fastest trajectory. Picture releasing a ball into a complex labyrinth. Rather than rolling down a single random hallway, the ball transforms into a wave, washing through every conceivable corridor at once before collapsing onto the quickest exit. Many experts think this is precisely how photosynthetic networks operate, avoiding pointless wandering by using quantum navigation. This discovery is mind-boggling precisely because these biological structures are hot, damp, and chaotic. Still, quantum coherence manages to hang on for picoseconds, a massive duration on a molecular scale, and more than enough to alter the final result. If greenery acts as quantum tacticians, it introduces a fascinating question. Has natural selection actively co-opted quantum physics? There is absolutely no logical barrier. preventing living systems from exploiting the exact same laws we observe in controlled physics experiments. Evolution has enjoyed billions of years of trial and error, meaning any species that stumbled upon a clever quantum hack for energy transfer, navigation, or sensory perception would have gained a massive survival edge. Regarding sensory perception, another biological enigma might rely on quantum explanations, our sense of smell. The traditional exposition relies on physical geometry, where a specific odor molecule slots into a nasal receptor perfectly, much like a key turning in a lock. However, this model has glaring flaws. Certain chemicals with nearly identical structures produce completely distinct odors, while drastically different shapes can trigger the exact same smell. A competing concept, the vibrational theory of olfaction, argues that our nasal receptors detect molecular vibrations rather than just physical contours. According to this model, once an odorant attaches to a receptor, electrons within the biological structure might quantum tunnel across the molecule, with the probability of tunneling relying heavily on the odorant's specific vibrational frequency. If correct, your olfactory system relies on quantum tunneling, the exact same phenomenon allowing particles to bypass barriers during nuclear fusion. Essentially, your nose could be processing scents in 2 dimensions at once, analyzing both physical structure and vibrational frequency to interpret the unseen chemical environment. Once again, this concept sparks intense debate, yet studies demonstrate that both human subjects and fruit flies can occasionally tell apart chemicals identical in every way, except for their vibrational frequencies. While not definitively proven, the results are certainly captivating. Quantum biology is still taking its first steps, relying mostly on daring hypotheses, preliminary trials, and an abundance of unresolved mysteries. However, the true thrill of this field goes beyond mere scientific curiosity. It serves as a powerful reminder that the bizarre laws governing the subatomic realm do not magically disappear outside of a laboratory. These principles extend directly into the plumage of migrating birds, the cellular structure of forest canopies, and the very air you inhale. It is a profoundly grounding realization that the identical mathematical formulas used to track isolated electrons in a vacuum also dictate the song of a robin and the glow of sunshine hitting a blade of grass. The natural world refuses to divide its disciplines. Quantum phenomena are not sequestered inside some tiny, isolated safe. They are deeply integrated into the fabric of living things. As we continue to decode these biological quantum hacks, we will likely unlock revolutionary technologies alongside a profound respect for the brilliance of natural selection. Living organisms, it turns out, have been utilizing the most bizarre instruments the cosmos has to offer all along. They simply never felt the need to explain it to us. While early pioneers left things unexplained, the reality is that microscopic matter behaves bizarrely. Tiny particles smear across superpositions, disrupt their own pathways, and juggle countless potential states simultaneously. This realm operates on likelihoods rather than guarantees. Yet glancing around reveals no hazy world of infinite maybe. You observe a solid coffee cup, a sturdy desk, and a cat that is definitively breathing or deceased, never both. Your environment feels remarkably stable and orderly. What causes this contrast? Why aren't chairs hovering in 2 spots simultaneously? Why doesn't your lunch remain a probability cloud until the fridge opens? The solution is decoherence, a subtle yet influential phenomenon. This process details how microscopic oddities shed their bizarre traits to form our familiar macroscopic reality. Picture one solitary electron in a superposition. Rather than sitting at a specific coordinate, it exists as a cloud of potential locations. Pinpointing its exact spot is impossible without a measurement, which merely prompts it to settle on one coordinate. Envision leaving that electron undisturbed in deep space. In total isolation, it maintains its fragile state of multiple possibilities. Down on Earth, however, absolute silence is impossible. Our environment is flooded with atmospheric gases, thermal energy, solar photons, colliding molecules, tremors, electromagnetic fields, and ambient radiation. The instant a microscopic entity bumps into these factors, its quantum harmony degrades. Crisp mathematical interference designs immediately become muddled. This is decoherence. The superposition isn't annihilated. Theoretically, it persists, but the entity becomes deeply intertwined with its surroundings. Every surrounding particle it brushes against gets woven into its blueprint. Once intertwined, the entity ceases acting like a secluded probability ripple and starts acting like a standard, foreseeable item. Microscopic states crave total secrecy, but the second their surroundings intrude, that secrecy evaporates. This isn't due to scientists prodding them with lab gear. Nature itself never stops observing. Gas molecules, photons, and tremors function as endless microscopic witnesses. Rather than forcing a total wave function collapse, they dilute the harmony, preventing interference. Think of this as a gradual wearing away rather than a sudden snap. It demands no aware human mind or grand measurement. It just requires brief exposure to the external environment, unfolding at astonishing speeds. Scientists can shield tiny components, like individual atoms, sufficiently to preserve their bizarre traits. However, for everyday items you can hold or consume, blending occurs in a flash. As an object gains mass and complexity, its microscopic oddities melt into macroscopic predictability much faster. In fact, the time frame for this blending in sizable items can be mere trillionths of a second. This rapid transition is why your sneakers never appear as a hazy cloud. Continuous environmental contact has already locked them into a concrete reality. Consequently, decoherence conceals superpositions rather than obliterating them. Theoretically, those blended states exist, but they are so thoroughly tangled with surrounding variables that retrieving them is impossible. They function entirely as normal items, despite their fundamental microscopic nature remaining intact. This also sheds light on a persistent physics riddle: the transition from likelihoods to concrete results. While decoherence doesn't dictate which specific result manifests, it clarifies the absence of microscopic interference in bulky items. It explains why a theoretical feline doesn't visibly flicker between life and death on your countertop. By leaking microscopic data into surrounding space, this process fabricates the appearance of a sudden collapse, creating a mathematical consensus. The underlying probability wave persists, yet it ceases exhibiting unified behavior, forming a vital link connecting the microscopic and macroscopic domains. Traditional physics remains incredibly practical for constructing overpasses, launching rockets, and baking soufflés. Yet, underneath, the cosmos vibrates with microscopic frequencies. Decoherence drapes a soft cover over this foundational bizarreness, generating the reliable realm we navigate. A great visualization is strolling across a frozen pond. Deep below, the liquid flows with microscopic fluidity. Meanwhile, the frozen top layer remains hard and dependable. Decoherence acts as the freezing mechanism. It doesn't banish the liquid below, it merely seals it away. The deeper an item's connection to its environment, the more impenetrable that frozen crust becomes. This carries massive implications for modern technology. Quantum computers must battle decoherence constantly. Their qubits are incredibly fragile, meaning a minor temperature shift or tiny vibration can ruin their delicate states. Engineers store them in intensely chilled, shielded chambers to preserve coherence. Failing to do so erases their computational advantage. Furthermore, this process influences how physicists interpret reality. Certain frameworks propose that a distinct probability collapse never happens. Instead, decoherence accounts for why specific results seem concrete. The cosmos isn't actively selecting a single path. Unchosen paths simply become invisible thanks to environmental tangling. The metaphorical tree still drops in the woods, but its echo is masked by background static. Decoherence doesn't untangle every physics mystery. It fails to clarify why one specific observation produces one specific outcome, or whether probability waves are physical entities or abstract calculations. However, it brilliantly details how microscopic bizarreness smoothly transitions into everyday reliability. It proves our visible environment isn't disconnected from the microscopic domain, but molded by it through endless engagement. Therefore, the next time you grab a mug or open a door, appreciate decoherence for ensuring those objects act as anticipated. It takes a cosmos of endless possibilities and delivers a solid handshake. It operates quietly in the background, no bright flashes or explosions, merely a steady, elegant fading of infinite options, leaving behind the dependable structures we call reality. While the macroscopic world settles into dependable structures, the microscopic realm holds surprises challenging our notion of sequence. Picture a test so bizarre that simply choosing when to look appears to ripple backward, altering previous events. You might mistake this for sci-fi, yet it represents the genuine reality of tests playing fast and loose with causality. Researchers call these mind-bending setups the quantum eraser and the delayed choice experiment. If you expected the subatomic realm to align with everyday logic, prepare yourself, because this is where chronology throws its hands up in defeat. To understand this, we revisit the classic double-slit arrangement. You shoot molecules, electrons, or photons toward a barrier featuring two narrow openings with a backdrop positioned to capture whatever emerges. When you ignore the specific route each item takes, an interference design of alternating bright and shadowy stripes appears, implying every entity traveled through both gaps simultaneously. However, the moment you introduce a sensor to track the exact opening each entity uses, those stripes vanish. Suddenly, the items strike the backdrop like tiny projectiles rather than rippling waves. Merely acquiring knowledge about the trajectory destroys the undulating nature of the entities. Everything is perfectly bizarre up to this point. Now we introduce a playful twist. Conceived by physicist John Archibald Wheeler, the delayed choice test involves arranging equipment without tracking the trajectory, while keeping the option to measure only after the entity clears the barrier. Essentially, you postpone your final call. Do you play the inquisitive sleuth or allow the entity to keep its enigmatic properties? This is where things turn dreamlike. The backdrop design perfectly aligns with your ultimate decision, even if made after the entity theoretically committed to its behavior. It feels as if the entity anticipates your choice and modifies its previous actions. It generates either wave stripes or projectile impacts dictated by a future circumstance. Wheeler's concept implies the subatomic environment refuses to lock into a definite state until compelled, applying to both location and chronology. Observation doesn't merely settle the result, it potentially writes the historical record. Naturally, researchers pushed boundaries further with the quantum eraser. Here, you tag entities to record their routes, but employ an ingenious method to wipe that data clean after they hit the backdrop. The moment you delete the trajectory details post-detection, the stripe design miraculously reappears. The entities retroactively resume wave-like conduct, acting as if they never surrendered their ambiguity. This introduces a discomforting concept. The physical world might remain unresolved until every piece of potential data is dealt with. This applies not just to the instant of measurement, but to how we subsequently handle that data. Think of it as a universal take on the famous feline paradox extended along the timeline. The animal's actual historical status hinges entirely on a choice made long after lifting the lid. How do we make sense of this? An appealing explanation proposes that data, rather than tangible substance, is the universe's fundamental currency. Subatomic results remain unfixed until you pose queries yielding definitive responses. Prior to that, every outcome stays tangled in a foggy broth of probability. This doesn't imply chronological travel is feasible or that we can rewrite history. Instead, it indicates our perception of chronology as a forward-moving avenue fails at the microscopic scale. Occurrences here aren't bound by neat chains of action and reaction, but exist within an interconnected network where results materialize only when evaluating the complete arrangement. Still, boundaries exist. These tests provide no mechanism for messaging yesterday or altering established history. Findings obey macroscopic causality, yet imply those laws possess more elasticity beneath the surface. Experts often explain this through correlation and entanglement, rather than direct causation. The entity isn't predicting your actions. Every component is simply linked so thoroughly that your final configuration dictates the visible designs. Alternative perspectives favor the block universe model, proposing every instant exists all at once, like pictures on a celluloid strip. From this angle, your decision isn't journeying into the past. It was perpetually woven into the eternal subatomic narrative. Meanwhile, plenty of researchers simply advise everyone to just do the math. The ultimate takeaway is clear. The cosmos has zero duty to align with our everyday assumptions regarding measurement, causality, or chronology. Our instincts evolved to handle large-scale items like felines, cups, and stones. Yet, deep within the subatomic fog, governing principles are far more nuanced, less straightforward, non-local, and incredibly bizarre. Testing delayed choices and erasing data doesn't shatter physics. It uncovers the complexity hiding underneath. These tests demonstrate the microscopic environment is far more than a tiny replica of our daily surroundings. It represents a distinct domain operating under unique logical principles. Whenever the clock seems to be messing with your head, keep in mind that at the subatomic scale, it almost certainly is. Building on that subatomic reality, imagine shrinking past swirling galaxies, diving through molecules, and slipping inside atoms. Eventually, you hit a realm where absolute certainty vanishes. Here, particles lack definite locations until observed, and every result is basically a cosmic dice roll. This is the quantum realm, a domain defined not just by its microscopic size, but by profound uncertainty. At the foundation of quantum theory, randomness doesn't just exist, it reigns supreme. This concept made Albert Einstein deeply uncomfortable, prompting his famous complaint that God doesn't play dice with the cosmos. For nearly a century, people have debated that quote in coffee shops while discussing physics and destiny. To understand his discomfort, we must look at what this randomness entails. Classical physics operates like a perfectly tuned engine. If you possess the exact speed and location of every piece in a system, you can forecast the future perfectly. It is a deterministic setup, much like setting up dominoes and knowing precisely how they will fall. Quantum theory shatters this predictable chain. Instead of exact forecasts, it relies on wave functions, mathematical tools outlining every potential particle behavior. The moment you measure the system, that wave function snaps into just one possibility. However, the specific result isn't pre-decided, it is authentically random. This isn't just a polite way of saying we lack data, nor is it caused by human error. This unpredictability is fundamentally stitched into existence. All physicists can do is calculate the likelihood of each result and embrace whatever happens. Frameworks like the many worlds interpretation try to sidestep this inherent randomness. They propose that every possibility actually occurs across infinitely splitting parallel realities. If you observe a particle spinning upward, an alternate you in a different universe sees it spinning downward. In that view, there is no true randomness, just endless actualized outcomes. Yet, even if this multiverse concept is accurate, you have no way to foresee which specific reality you will personally experience. From your perspective, life remains completely unpredictable. This sparks intense philosophical debates. If pure chance sits at the bedrock of existence, how does that impact cause and effect, free will, or the rules of nature? It can be jarring to realize the cosmos isn't following a rigid screenplay, but rather improvising, leaving a basic looseness in reality's tapestry. However, randomness does not equal total chaos. Quantum mechanics delivers incredibly exact forecasts. It doesn't claim anything is possible. Rather, it provides a specific menu of options with exact probabilities. When researchers verified theories like quantum electrodynamics, their predictions matched physical experiments up to 12 decimal places. That is equivalent to guessing Mount Everest's exact height down to the thickness of a human hair. While individual quantum events are random, the overarching framework is remarkably organized. Think of tossing 100 dice. Every single die lands randomly, but the combined total consistently hovers around a predictable average. Because massive particle groups behave so dependably, the solid rules of classical physics emerge. This reliability is why your coffee cup doesn't spontaneously quantum tunnel through your desk, even though individual atoms technically could. Viewed this way, chance isn't a glitch. It is a vital feature. It injects adaptability and novelty into the cosmos, acting as the crucial ingredient for consciousness, creativity, and life. Consider biological evolution. If every biological process was strictly pre-programmed, we would have no variation. But introduce a dash of quantum chance, a random genetic tweak or spontaneous molecular shift, and suddenly nature has new pathways. Some paths produce leaves, others create leopards, and some lead to philosophers. Within the quantum domain, chance acts as the ultimate driver of diversity, spinning complexity from simplicity without violating physical laws, simply because quantum rules are statistical rather than prescriptive. Many thinkers find deep comfort in this lack of absolute certainty. A strictly deterministic cosmos can feel like a mechanical jail, where every emotion and thought is merely the inevitable ripple of atoms following rigid instructions. A probability-based universe allows for genuine surprises, pulling outcomes from a shuffled deck. Naturally, this chance brings profound mystery. Why does a particle choose one state over another? Quantum theory provides no underlying reason, only statistical odds. It is like flipping a coin and watching it land on heads. There is no hidden reason other than a 50% chance. This implies the cosmos can never be fully understood classically. We hit a hard ceiling of certainty, a threshold where definitive answers stop and only spectrums of probability begin. Despite this, humanity flourishes within that uncertainty, harnessing it to build technologies and extract profound meaning. This unpredictability also guarantees absolute identical copies cannot exist. Even identically repaired particles will occasionally produce different results. This minuscule irregularity is precisely what keeps reality dynamic. So maybe the universe really does roll the dice, but it plays with such elegance that it manifests time, thoughts, atoms, and galaxies. We might never completely control this fundamental chance, but we can value it not as a defect in the cosmic engine, but as the gentle, vibrant hum of pure potential woven into the essence of everything. Embracing this pure potential leads us to a profound realization. Even if this field of study were just a collection of bizarre yet beautiful mathematical formulas, it would still stand as a monumental triumph of human intellect. However, its true magic lies far beyond mere math. Rather than just mapping out odds and subatomic bits, it prompts us to ponder the very nature of existence and comprehension. By stripping away the cosmic layers, this science doesn't merely hand us fresh solutions, it fundamentally alters the inquiries we make. We usually picture the physical world as a rigid, permanent structure that persists regardless of our presence. Yet the subatomic realm politely but firmly challenges this notion. It implies that on the most microscopic level, nothing is truly set in stone. Instead, existence resembles a collection of latent opportunities, much like slumbering visions awaiting a watcher to bring them to life. Consider a particle in superposition. It isn't simply hesitant to pick a state. It actively occupies every potential condition simultaneously. Rather than a distinct point, it forms a blurry cloud of likelihood. Then, the moment we measure it, it locks into a single result, almost as if the cosmos takes a deep breath and selects a specific narrative. This phenomenon introduces a subtly profound question. Given that the act of observation so heavily influences the final result, are we truly isolated from the cosmos, or are we deeply woven into its intricate, interconnected choreography? While scientists treat these concepts as technical puzzles, everyday people often find them deeply spiritual. Still, we shouldn't treat this science as a quick path to enlightenment, or an endless source of metaphors for self-help books. Instead, it grants us a vital gift: modesty. It proves that our daily assumptions regarding causality, matter, time, and space do not hold the ultimate truth. The ordinary environment we navigate each day is merely a single interpretation of existence, filtered by our evolutionary history, shaped by our sensory inputs, and stitched together by routine. Consequently, this discipline transcends mere physics. It acts as a reflective surface, highlighting the boundaries of our comprehension, the limits of our intellect, and the breathtaking oddity of our cosmic home. Consider the famous feline paradox. Rather than viewing it as an actual animal caught in a logical trap, see it as an analogy for navigating life's unpredictability. We are constantly juggling contradictory outcomes, partial truths, and near guarantees. Whether you are anticipating medical test results, hoping for a new job, or just guessing about tomorrow's rain, you frequently inhabit your own state of superposition. You balance dread and optimism, skepticism and anticipation. These various outcomes stack softly upon one another until a decision or the passage of time forces the wave to collapse. Perhaps this reveals the hidden charm of the subatomic world. It doesn't declare existence to be meaningless. It simply shows that existence has no duty to be easily understood. There is a gentle liberation in accepting this. When absolute surety isn't guaranteed, strict limitations vanish as well. Since the world remains undefined until it is observed, endless possibilities stay alive, flickering just out of view. The very term quantum itself carries a kind of poetic weight. Derived from the Latin word quantus, it asks, how much? How much energy or light is a specific particle permitted to exhibit? Furthermore, the term highlights strict borders and separate, indivisible packets. It represents the smallest allowed unit of transformation. This concept holds deep significance. Amidst the sprawling confusion of the universe, there are quiet thresholds and minimum steps that must be surpassed. The cosmos isn't entirely continuous. Certain transformations happen in sudden leaps. Think about dreaming. You don't construct a dreamscape one single atom at a time. You instantly leap into non-existent worlds, witnessing the impossible until it feels completely natural. Upon waking, you might forget the specific rules, but you carry back the sensation of boundless opportunity. Studying the subatomic world evokes a similar feeling, akin to rising from sleep and discovering that reality is far weirder, wilder, and more wonderful than you ever guessed. Naturally, this lack of predictability can be a little unsettling. Human beings crave cause and effect, finding comfort in absolute certainty. Yet, perhaps certainty is slightly overrated. Maybe it is perfectly fine to embrace unresolved mysteries, to stroll through a woodland of probabilities without demanding to know which tree is authentic. Perhaps true wonder resides exactly in the gap between what we can firmly grasp and what we can only vaguely glimpse. As the brilliant physicist Richard Feynman famously remarked, "I think I can safely say that nobody understands quantum mechanics." He intended this statement to be both humorous and entirely accurate. Even the experts who calculate these formulas daily and build models from its predictions will admit that you don't comprehend this field through conventional means. You embrace it much like you would a beautiful poem or a vivid dream. The math is precise and testable, yet it completely rejects standard logical frameworks. Ultimately, this refusal to conform makes it incredibly honest, because the universe was never obliged to be simple. It just had to be. So, as we drift now through these quiet ripples of subatomic philosophy, the ultimate takeaway might not concern particles or odds, but rather our point of view. We must learn to view unpredictability as an essential feature rather than a broken flaw. We need to gently release our obsession with total comprehension, finding peace in the beautiful truth that we belong to a cosmos that is continuously unfolding, choosing and shimmering with latent opportunities. It is a realm where the most barren vacuum isn't truly empty, where the flow of time can flex, where light forgets how to behave, and where, in the end, reality dreams too. As reality gently drifts into that beautiful dreamscape, I want to express my deepest gratitude for your presence here tonight. Whether your mind remains fully alert, is slowly fading into deep relaxation, or has already wandered halfway into a dream, we have covered an incredibly long distance together. Our shared expedition has guided us past tiny cuts in cardboard, feline paradoxes in imaginary boxes, undulating energy fields and bizarre temporal erasers. We have encountered entities that blur the line between particle and wave, alongside fundamental forces governed by an alphabet we are only just beginning to decipher. Yet, somewhere along this incredible route, the sheer weirdness of the subatomic realm slowly revealed its quiet, underlying elegance. Initially, these concepts might feel entirely disconnected from reality. A cosmos where existence requires an observer, where the boundaries of causality dissolve, and where a single entity can occupy multiple locations simultaneously. However, the continuous lesson of quantum mechanics is that our tangible, measurable environment is merely the outer layer. Underneath this familiar surface exists a much gentler reality. It is undoubtedly peculiar, yet it remains remarkably adaptable, open to wonder, and constructed entirely from glowing potential rather than rigid absolutes. Furthermore, we are not detached spectators looking through a window. We are fundamentally woven into this very fabric. The atoms comprising your fingertips, the photons bouncing off your eyes, and the oxygen filling your lungs are all governed by these exact same probabilistic rules. You do not simply exist within the cosmos. You are an intrinsic expression of it, which carries a profoundly poetic resonance. Perhaps you are currently curled up beneath a heavy blanket, staring upward at the ceiling with your thoughts flickering like stars, or simply finding yourself far from home or far from sleep. Regardless of your physical location, the hope is that this exploration has provided something soft, strange, or simply still. When we peer directly into the core of physical substance and question what is truly real, this field of science does not hand us a final answer. Instead, it presents a shifting mirror, demonstrating that knowing something deeply does not always mean understanding it completely. It shows us that inquiries hold just as much elegance as solutions, and that mystery is an essential feature rather than a failure. While it is tempting to desire straightforward rules and absolute fairness from the universe, there is a unique comfort hidden within this tangled uncertainty. It whispers a gentle truth saying, "You do not need all the answers to feel at home here," because even if the particles are uncertain, the present moment you are in is entirely real. The breath you just took, the thought that just drifted by, and the weight of your body gently sinking into stillness. That is quantum too, and it is enough. So, thank you for giving your time, your ears, and your quiet curiosity to this little exploration. Thank you for trusting the strangeness and for sitting comfortably with the not knowing. And if you have already fallen asleep, that is absolutely wonderful. The quantum world will still be right here waiting when you wake.